Hello there, and welcome to another gentle journey into the cosmos, where mysteries unfold like whispered secrets, and the universe reveals its most intriguing puzzles. Tonight, we're drifting towards something extraordinary, something that has astronomers around the world both fascinated and quietly unsettled. Before we begin our exploration, I'd love to know where you are right now, gazing up at the same sky that holds our visitor, and what thoughts cross your mind when you consider that we might not be alone in watching the stars. If you find comfort in these cosmic contemplations, or if the vastness of space helps quiet the busy thoughts of your day, I'd be grateful if you'd give this video a gentle thumbs up. It helps others discover this peaceful corner of the universe where curiosity meets tranquility, and perhaps they too will find solace in the grand questions that dance between the stars. Now, settle in. Let your breathing slow and prepare to meet something that shouldn't exist, yet does. Because somewhere beyond the familiar glow of our solar system's edge, traveling at speeds that defy casual explanation, comes an object that has scientists questioning everything they thought they knew about cosmic visitors. Its name is 3I/ATLAS, and if current theories hold even a whisper of truth, it might be watching us just as intently as we are watching it. On July 1st, 2025, the darkness of space revealed one of its most puzzling secrets. Deep in the Chilean mountains, the robotic eye of the Atlas telescope swept across the southern sky in its endless vigil, searching for objects that might threaten our small blue world. But what it discovered that night wasn't quite what anyone expected. Moving against the stellar backdrop at an impossible speed of 152,000 miles per hour came something that would challenge our understanding of what travels between the stars: the asteroid terrestrial impact. Last Alert System, or ATLAS as it's affectionately known, is humanity's most sophisticated early warning network for cosmic threats. Picture 4 robotic sentinels stationed across our planet, from the volcanic peaks of Hawaii to the clear skies of South Africa and Chile, each one equipped with cameras so powerful they can survey nearly the entire visible sky every single night. These aren't your typical backyard telescopes. Each Atlas station uses a 50-centimeter Wright-Schmidt telescope paired with a 110-megapixel camera, creating a field of view 15 times wider than the full moon appears to us. The system works with mechanical precision and digital patience. It divides the heavens into 1,500 distinct patches, then photographs each patch 4 times over the course of several minutes. Computers analyze these image quartets, searching for anything that moves, anything that changes position against the seemingly fixed stars. Most discoveries turn out to be familiar neighbors, asteroids and comets, whose orbits are well understood and pose no threat. But occasionally, very occasionally, something appears that doesn't fit the patterns we've come to expect. When Atlas detected 3I/Atlas, the computers immediately recognized something unusual. This wasn't following the gentle elliptical dance that characterizes objects born within our solar system's embrace. Instead, its trajectory traced a hyperbolic path, the mathematical signature of something that came from the vast spaces between the stars. Within hours, astronomers around the world were alerted to what would become only the 3rd confirmed interstellar object ever discovered passing through our cosmic neighborhood. The designation itself tells a story. The 3I marks it as the 3rd interstellar visitor we've catalogued, following the mysterious cigar-shaped Oumuamua in 2017 and the more comet-like Borisov in 2019. The Atlas portion honors the survey that found it, a fitting tribute to the technological marvel that made this discovery possible. But names and numbers only begin to capture what makes this visitor so extraordinary. Size matters in the cosmos, and 3I/ATLAS is a giant among interstellar wanderers. Where Oumuamua measured perhaps 400 meters at its longest, and Borisov stretched maybe a kilometer across, 3I/ATLAS spans over 3 miles in diameter. Its estimated mass exceeds 33 billion tons, making it thousands of times more massive than its predecessors. To put that in perspective, if Oumuamua was a pebble skipping across a cosmic pond, 3I/ATLAS would be a boulder crashing through the same waters. This dramatic difference in scale troubles astronomers in ways that extend far beyond simple curiosity. According to our models of how planetary systems form and evolve, smaller debris should be far more common than large objects when it comes to material ejected into interstellar space. We should have discovered thousands, perhaps hundreds of thousands, of objects the size of Oumuamua before encountering something as massive as 3I/Atlas. Yet here it is, defying statistical expectations and challenging our understanding of what wanders the galaxy between the stars. Harvard astrophysicist Avi Loeb, never one to shy away from unconventional theories, has suggested that the size discrepancy alone warrants serious consideration of possibilities beyond natural explanations. In his characteristically direct style, Loeb points out that we shouldn't judge this cosmic visitor based solely on surface observations. Just as you wouldn't assess a book by examining only its cover, the true nature of 3I/ATLAS might require looking deeper than its apparent composition of ice, dust, and organic compounds. The path that brought 3I/ATLAS to our attention is itself a marvel of cosmic mechanics. Its orbit carries an eccentricity of 6.141, a number that speaks to trajectories shaped by forces far beyond our Sun's gravitational influence. For context, any object with an eccentricity above 1 is traveling fast enough to escape our solar system entirely. Oumuamua registered about 1.2, while Borisov came in at 3.6. The extreme eccentricity of 3I/ATLAS suggests it's been accelerated by encounters with massive structures during its journey through the galaxy, nudged along by the gravity of giant molecular clouds, or perhaps the collective pull of stellar associations. When astronomers trace its path backward through time and space, 3I/ATLAS appears to have originated from the thick disk of our Milky Way galaxy, a region populated by ancient stars formed when the universe was younger and contained fewer heavy elements. Age estimates suggest this visitor has been traveling through space for approximately 4.6 billion years, making it a contemporary of our own solar system's formation. Unlike the relatively youthful Oumuamua, which appears to be only about 1 billion years old, 3I/ATLAS carries with it the accumulated experience of eons spent crossing the vast emptiness between the stars. This ancient heritage raises profound questions about the journey that brought it here. During its billions of years of travel, 3I/ATLAS would have encountered countless gravitational influences, passed through regions of varying stellar density, and potentially witnessed the birth and death of entire stellar populations. If it harbored any form of dormant life, or carried within it the seeds of biological or technological processes, the sheer span of time involved suggests possibilities that stretch the boundaries of conventional thinking. NASA's response to 3I/ATLAS has been nothing short of comprehensive. The space agency has mobilized an unprecedented array of observational assets, creating what amounts to the most intensive study of an interstellar object in human history. The Hubble Space Telescope, with its decades of proven performance, captured the first detailed images of the visitor's distinctive teardrop-shaped coma. The James Webb Space Telescope, humanity's newest and most powerful space-based observatory, turned its infrared eyes toward the object to peer through the dust and gas surrounding its nucleus. The Transiting Exoplanet Survey satellite, normally dedicated to hunting for planets around distant stars, redirected its attention to monitor 3I/Atlas for any unusual variations in brightness that might hint at rotation patterns or structural changes. The Swift Observatory, designed to catch the most energetic explosions in the universe, focused its ultraviolet instruments on detecting the subtle signatures of sublimating gases in the object's coma. Even more intriguingly, missions throughout the solar system have been tasked with observations. The Perseverance rover on Mars, the Mars Reconnaissance Orbiter, and the venerable Curiosity rover have all been enlisted to provide different perspectives as the object passes through the inner solar system. The Europa Clipper mission, currently en route to Jupiter's icy moon, will observe from the outer system. The Parker Solar Probe, humanity's fastest spacecraft, will monitor from its position near the Sun. This coordinated effort extends beyond American assets. The European Space Agency's Solar and Heliospheric Observatory, a joint venture with NASA, contributes its unique vantage point from the first Lagrange point between Earth and the Sun. Ground-based observatories from Chile's Atacama Desert to Hawaii's Mauna Kea have joined the global surveillance network, creating a comprehensive monitoring system that tracks 3 I/ATLAS across multiple wavelengths of light and through various phases of its journey. The SETI Institute's Allen Telescope Array, typically focused on searching for signs of intelligent life around distant stars, has turned its attention much closer to home. Led by Dr. Wael Farah, the team began monitoring 3 I/ATLAS within 24 hours of its discovery, scanning for both natural radio emissions and any potential technological signatures. Within just 1 week, the array had collected over 21 terabytes of data, an amount equivalent to thousands of hours of high-resolution video. This digital treasure trove is currently being analyzed with unprecedented care, searched for patterns that might distinguish between natural cosmic phenomena and something more deliberately constructed. The radio observations represent more than scientific curiosity. They embody humanity's careful approach to the unknown, simultaneously hoping to understand and quietly preparing for possibilities that extend beyond conventional astronomy. Every frequency scan, every data analysis session, carries with it the weight of questions that have haunted human consciousness since we first looked up at the night sky and wondered if anything might be looking back. As July melted into August of 2025, telescopes around the world began detecting the chemical fingerprints of 3 I/ATLAS. The Gemini South Telescope and NASA's Infrared Telescope Facility identified water ice sublimating from the object's nucleus, the expected signature of a comet awakening as it approaches the warmth of our Sun. Ultraviolet observations by the Swift Observatory confirmed the presence of water vapor and hydroxide ions in the growing coma, while the James Webb Space Telescope revealed unusually high concentrations of carbon dioxide mixed with smaller amounts of water ice, carbon monoxide, and carbonyl sulfide. More intriguing discoveries followed. The Very Large Telescope in Chile's Atacama Desert detected cyanide gas and atomic nickel vapor streaming from the nucleus, concentrations similar to those observed in comets born within our own solar system. But there was an anomaly that caught the attention of spectroscopists worldwide. While nickel emission appeared as expected, iron vapor remained notably absent from the observations. In typical solar system comets, nickel and iron appear in roughly equal proportions when outgassing occurs, their abundance patterns linked to the original composition of the primordial material from which comets formed. The absence of iron in 3 I/ATLAS suggests either an unusual formation environment or perhaps processing that occurred during its billions of years of interstellar travel. Cosmic rays, the high-energy particles that pervade the space between stars, can slowly alter the surface composition of objects over such vast timescales. Alternatively, the chemical signature might reflect conditions in the stellar nursery where 3 I/Atlas originated, a place and time when the galaxy's thick disk contained different proportions of heavy elements than we observe in younger stellar regions today. Throughout August, astronomers documented what they described as a rapid and steady increase in both nickel and cyanide concentrations within the object's coma. This escalating outgassing activity marked 3 I/Atlas as behaving much like a typical comet, responding to increasing solar heating as it approaches the inner solar system. Yet the sheer scale of the object, combined with its unusual chemical fingerprints and extraordinary origin story, keeps nagging questions alive in the minds of researchers who have spent their careers studying the more predictable inhabitants of our cosmic neighborhood. The visual appearance of 3I/ATLAS tells its own compelling story. Through the patient eye of the Hubble Space Telescope, we see not just a point of light, but a complex structure that challenges our preconceptions about what interstellar visitors should look like. The comet presents itself as a teardrop-shaped cocoon of dust and gas, stretching approximately 26,000 kilometers from head to tail, roughly twice the diameter of our entire planet. This gossamer envelope, delicate as morning mist, yet spanning continental distances, serves as both revelation and veil. Within this ethereal shroud, two distinct populations of particles follow their own choreographed dance. Smaller dust grains, each no wider than a bacterium, rocket away from the hidden nucleus at speeds of 22 meters per second, propelled by the gentle but persistent pressure of sublimating ice. Meanwhile, larger particles, hefty by microscopic standards at 100 micrometers across, lumber through the coma at the more leisurely pace of 2 meters per second. This size-dependent velocity distribution creates layers within layers, a cosmic onion of complexity that reveals itself only to the most careful observers. The reddish hue that suffuses the entire structure speaks to chemistry written in starlight. This rusty coloration, similar to what we observe in certain asteroids within our own solar system and in the previous interstellar visitor Borisov, likely arises from organic compounds called tholins. These molecules form when simpler carbon-based substances endure eons of bombardment by cosmic radiation, slowly transforming into the complex organic chemistry that gives 3I/ATLAS its distinctive appearance. But this familiar coloration, rather than providing comfort, instead raises questions about the deep processes that shape matter during billion-year journeys through the galaxy's emptiness. Behind this dusty veil lies the object's true heart, its solid nucleus, hidden from direct observation by the very activity that makes it detectable. Every second, according to Hubble's careful measurements, approximately 66 kilograms of material stream away from this concealed core, carrying with them the chemical signatures that tantalize and puzzle astronomers in equal measure. This ongoing mass loss, while substantial by earthly standards, represents merely a whisper compared to the object's total bulk of 33 billion tons. The mathematical precision of 3I/ATLAS's trajectory reveals gravitational influences that extend far beyond our local stellar neighborhood. Its path through space carries the accumulated signatures of encounters with massive molecular clouds, stellar associations, and perhaps close passages by other stars during its multi-billion-year odyssey. Each gravitational encounter left its mark on the object's velocity and direction, creating the specific combination of speed and trajectory that would eventually bring it to our attention in the summer of 2025. This ancient wanderer approaches our solar system from what astronomers call a retrograde orbit, traveling in the opposite direction to the general motion of planets around our Sun. This orientation offers certain advantages that have not escaped the notice of researchers studying theoretical interstellar navigation. A retrograde approach allows for more efficient gravitational interactions with multiple planets, potentially enabling course corrections or velocity changes that would be impossible with a prograde trajectory. For a natural object shaped by random gravitational encounters, such an orientation might be merely coincidental. For something with more deliberate origins, it could represent optimal mission planning. The timing of 3I/ATLAS's approach carries its own subtle implications. The object will reach its closest point to the Sun on October 29, 2025, positioning itself at a distance of approximately 102 million kilometers from our star. This perihelion distance places it well outside the orbit of Mars, but comfortably within the realm where solar heating can drive the dramatic outgassing that creates its visible coma and tail. More significantly, this timing means that during its closest approach to the inner solar system, 3I/ATLAS will pass behind the Sun as viewed from Earth, creating a natural eclipse that will temporarily hide it from our most powerful ground-based telescopes. This solar conjunction, lasting from late September through early December, creates what intelligence analysts might recognize as a perfect surveillance window. During these months, any activities occurring in the vicinity of 3I/ATLAS would be shielded from terrestrial observation by the overwhelming brightness of our own star. Ground-based telescopes would be effectively blinded, and even space-based observatories would face significant challenges in maintaining continuous monitoring. The object would emerge from this hidden period having completed whatever processes, natural or otherwise, might occur during its intimate encounter with our solar system's heart. The concept of gravitational maneuvers during solar conjunction isn't merely theoretical speculation. Aerospace engineers have long recognized that close approaches to massive objects like the Sun offer opportunities for what's known as the Oberth effect, where a spacecraft can achieve maximum efficiency by firing its engines at the point of closest approach. The intense gravitational field amplifies any propulsive effort, allowing for dramatic changes in velocity with minimal fuel expenditure. For an interstellar probe designed to enter a new stellar system, a reverse Oberth maneuver could provide the perfect opportunity to shed excess velocity and potentially establish a permanent presence within that system. The orbital characteristics of 3I/Atlas reveal another intriguing detail that has captured the attention of astrodynamics specialists. The object's path carries it surprisingly close to several planets in our solar system, with encounter probabilities that statistical analysis suggests should occur less than once in every 2,000 similar trajectories. Venus, Mars, and Jupiter all lie within the object's extended sphere of gravitational influence, offering multiple opportunities for observation, course correction, or data collection that would be invaluable to any reconnaissance mission. These close planetary encounters also provide natural explanations for any unexpected changes in the object's trajectory that might be observed in the coming months. Should 3I/ATLAS deviate from its predicted path, gravitational perturbations from these planetary interactions could mask more deliberate course corrections. The ambiguity inherent in such a complex gravitational environment offers what military strategists would recognize as perfect operational camouflage, where natural phenomena provide cover for activities that might otherwise attract unwanted attention. The age of 3I/ATLAS, estimated at 4.6 billion years, places its origin at a time when our own solar system was still condensing from the primordial nebula that would eventually birth the Sun and planets. During its subsequent journey through the galaxy, this ancient traveler would have witnessed the formation and evolution of countless stellar systems, potentially gathering information about the development of planetary environments across vast regions of our galactic neighborhood. If it carried within its structure any form of data storage or recording capability, the accumulated observations from such an extended reconnaissance mission would represent an intelligence treasure trove beyond current human comprehension. The chemical composition revealed by spectroscopic analysis, while generally consistent with natural comet-like processes, contains subtle anomalies that keep alternative theories alive in scientific discussions. The absence of iron in the outgassing signature, the unusual proportions of organic compounds, and the specific patterns of volatile release all fall within the range of natural variation observed in solar system comets, yet they also represent exactly what we might expect from artificial materials designed to mimic natural processes while serving other purposes. Contemporary theories about interstellar exploration suggest that any advanced civilization attempting to study distant stellar systems would likely design their probes to blend seamlessly with the natural debris commonly found in space. A reconnaissance vehicle masquerading as a comet would face minimal interference from the target civilization while gathering comprehensive data about planetary environments, atmospheric compositions, and the technological capabilities of any resident species. The perfect camouflage would be indistinguishable from naturally occurring objects until subjected to the most detailed analysis. As autumn approaches and 3I/Atlas continues its steady approach toward the inner solar system, the global astronomical community maintains its vigilant watch. Every night that weather permits, telescopes around the world turn their attention to this mysterious visitor, recording its brightness variations, monitoring its spectral signature, and documenting the subtle changes that mark its gradual awakening under the increasing warmth of our sun. Yet beneath the routine scientific observations lies an undercurrent of anticipation, a quiet awareness that we may be witnessing something far more significant than the mere passage of an ancient piece of cosmic debris. The question that hovers unspoken in observatory control rooms and scientific conferences around the world is not merely what 3I/ATLAS might be, but what it might be seeing as it conducts its own observations of our solar system. If this visitor carries within it any form of sensing capability, artificial or biological, it now occupies the perfect position to study our planet, our civilization, and our technological development with the same intensity that we direct toward understanding its own nature. The surveillance capabilities that 3I/ATLAS might possess, should it indeed be more than a wandering remnant of ancient stellar formation, would far exceed anything in humanity's current technological arsenal. From its vantage point in the depths of space, traveling through the solar system at velocities that dwarf our fastest spacecraft, such a visitor would have access to observational opportunities that ground-based civilizations can only dream of achieving. Consider the perspective that billions of years of interstellar travel would provide. During its journey through the galaxy's thick disk, 3I/ATLAS would have encountered stellar systems in various stages of evolution, from young star-forming regions where planets were still accreting from primordial disks, to ancient systems where stellar evolution had long since determined the fate of any orbiting worlds. Each encounter would have offered lessons in planetary development, atmospheric evolution, and perhaps most intriguingly, the signatures that mark the presence of technological civilizations. The accumulated experience from such an extended reconnaissance mission would create an intelligence database of staggering proportions. Spectroscopic signatures that reveal atmospheric compositions, radio emissions that betray the presence of technology, thermal patterns that suggest industrial activity, and orbital mechanics that distinguish natural satellites from artificial constructs would all become familiar patterns to a visitor that had observed thousands of stellar systems during its galactic wanderings. Now, as 3I/ATLAS approaches our own solar system, it occupies the ideal position to conduct a comprehensive survey of everything that makes our cosmic neighborhood unique. Its trajectory carries it through the plane of the ecliptic, the flat disk where all major planets orbit, providing optimal viewing angles for observing planetary characteristics, moon systems, and the subtle gravitational influences that shape the architecture of our solar family. From its current position, roughly 277 million miles from Earth when first imaged by Hubble, 3I/ATLAS enjoys an unobstructed view of our planet's day and night cycles, weather patterns, and the electromagnetic signatures that leak into space from our technological civilization. The radio waves that carry our television broadcasts, cellular communications, and radar systems spread outward from Earth at the speed of light, creating an ever-expanding sphere of artificial signals that would be clearly detectable to any sufficiently sensitive instruments. Our planet's atmosphere tells its own detailed story to any observer equipped with spectroscopic capabilities. The presence of oxygen, in concentrations far above what geological processes alone could maintain, serves as a beacon for biological activity, while the simultaneous presence of water vapor, methane, and other trace gases creates a chemical fingerprint that virtually shouts the presence of a living world. More subtly, the seasonal variations in atmospheric composition, driven by the growth and decay of vegetation across Earth's continents, would reveal the rhythms of a biosphere in full bloom. The artificial satellites that orbit our planet in ever-increasing numbers would present their own fascinating puzzle to an external observer. The precise geometric patterns of geosynchronous communication satellites, the polar orbits of Earth observation platforms, and the complex choreography of low Earth orbit constellations would clearly distinguish artificial objects from natural phenomena. The thermal signatures, reflective properties, and radio emissions from these human-made objects would provide detailed insights into our technological capabilities and priorities. Perhaps most revealing would be the patterns of human activity visible in our planet's night-side illumination. The concentration of artificial lighting in major population centers, the linear patterns that trace our transportation networks, and the industrial complexes that burn with characteristic thermal signatures would create a detailed map of human civilization visible from interstellar distances. The growth and change in these patterns over the months of observation would reveal the dynamic nature of our technological society and provide estimates of our developmental trajectory. The Moon, our constant companion, would offer its own insights to a careful observer. The precise nature of its orbit, clearly modified by human activity through the presence of artificial satellites and the distinctive thermal signatures of past landing sites, would indicate a species that has already begun to extend its reach beyond its home planet. The subtle but detectable changes in the lunar surface, marked by human exploration and the debris left behind by decades of space missions, would suggest a civilization in the early stages of spacefaring capability. Our neighboring planets would provide additional context for understanding the development of our solar system and the unique characteristics that make Earth hospitable to complex life. Mars, with its thin atmosphere and seasonal polar caps, shows clear evidence of a world that once possessed more substantial atmospheric conditions. The sophisticated robotic explorers currently roving its surface would be easily detectable to external observation, their systematic exploration patterns and communication signals marking them as artificial constructs engaged in scientific investigation. Venus, shrouded in its dense atmospheric veil, would present a study in runaway greenhouse effects and the delicate balance that determines planetary habitability. The occasional artificial visitors that brave its hostile environment to conduct brief surface missions would stand out clearly against the natural background, their brief operational periods and characteristic signatures marking them as technological artifacts rather than natural phenomena. The gas giants of the outer solar system, with their complex moon systems and dynamic atmospheric phenomena, would provide insights into the processes that shape planetary formation and evolution. The artificial spacecraft currently exploring these distant realms, from the Cassini mission's extended study of Saturn to the various probes that have ventured into the Jovian system, would be visible as tiny but unmistakably artificial points of light and radio emission against the cosmic background. Most intriguingly, any observer with sufficient technological sophistication would likely detect the subtle but persistent stream of artificial objects that humanity has launched beyond the boundaries of our solar system. The Voyager probes, Pioneer spacecraft, and New Horizons mission all carry their own distinctive signatures as they continue their journeys into interstellar space. These ambassadors of human civilization, while tiny compared to natural cosmic phenomena, would serve as clear indicators of a species that has achieved the capability to send its creations beyond the gravitational boundaries of its birth system. The timing of 3I/A TLAS's visit coincides with a particularly active period in human space exploration. Multiple Mars rovers operate simultaneously on the red planet's surface. The James Webb Space Telescope has revolutionized our understanding of distant cosmic phenomena, and ambitious plans for lunar bases and Mars colonization are transitioning from science fiction to engineering reality. An external observer would witness humanity at a crucial inflection point in its technological development, poised to become a truly spacefaring civilization. The electromagnetic spectrum tells an even richer story of human activity. Our planet broadcasts its technological sophistication across multiple wavelengths, from the long-wave radio signals that bounce off the ionosphere to the microwave emissions of cellular networks and satellite communications. The patterns, frequencies, and modulation schemes used in these transmissions would provide detailed insights into our information processing capabilities, communication protocols, and the underlying mathematics and physics that govern our technology. More subtly, the industrial processes that power human civilization leave their own distinctive signatures in the atmospheric composition and thermal emissions observable from space. The carbon dioxide concentrations that mark our use of fossil fuels, the trace gases released by manufacturing processes, and the heat signatures of major industrial centers would all be clearly visible to sufficiently advanced sensors. The seasonal and geographic variations in these signatures would reveal the global nature of human civilization and the interconnected systems that support our technological society. The space-based infrastructure that increasingly supports human activities would present a particularly fascinating study for an external observer. The International Space Station, with its regular crew rotations and constant stream of supply missions, demonstrates our capability to maintain permanent human presence beyond Earth's surface. The growing constellation of Earth observation satellites reveals our systematic efforts to monitor and understand our home planet's environmental systems. Military and intelligence satellites, while often designed to operate with minimal detectability, would still be observable to sufficiently advanced sensors through their orbital characteristics, periodic communication bursts, and the thermal signatures of their onboard systems. The global positioning system that enables precise navigation and timing for civilian and military applications would be clearly recognizable as an artificial constellation designed to provide planet-wide coverage. The deep space tracking networks that monitor our interplanetary missions would themselves be detectable as powerful radio sources with highly directional transmission patterns. The systematic scanning motions of these antenna arrays and their coordinated observations of specific celestial targets would mark them as artificial constructs engaged in space surveillance and communication activities. Perhaps, most significantly, any observer with the capability to monitor our scientific activities would witness humanity's accelerating efforts to understand our cosmic environment. The radio telescopes that search for signals from other civilizations, the space-based observatories that peer deep into the universe's history, and the particle accelerators that probe the fundamental nature of matter and energy would all serve as indicators of a species actively engaged in expanding its knowledge of the universe. The patterns of human space exploration reveal strategic thinking and long-term planning that would be recognizable to any civilization that had achieved interstellar travel capabilities. Our systematic exploration of the solar system, from the inner planets to the outer moons and asteroid belt, demonstrates methodical scientific investigation combined with resource assessment and technological development. The progression from simple flyby missions to orbital surveys to surface operations would be familiar to any species that had followed a similar developmental path. The international cooperation that characterizes many of our most ambitious space missions would also be notable to external observers. The collaborative nature of projects like the International Space Station, the coordination required for Mars exploration missions, and the shared scientific data from space-based observatories would indicate a species capable of transcending tribal boundaries when pursuing common goals. Yet alongside these cooperative efforts, the competitive aspects of human space activities would be equally apparent. The national flags planted on the lunar surface, the military applications of satellite technology, and the strategic implications of space-based capabilities would reveal the complex political dynamics that still characterize human civilization. Any observer with historical experience of civilizational development would likely recognize these patterns as typical of species in the early stages of achieving spacefaring capability. The rate of change in human space activities would provide insights into our technological development trajectory and the potential timescales for achieving more advanced capabilities. The accelerating pace of satellite deployments, the increasing sophistication of planetary exploration missions, and the growing commercial involvement in space activities would all suggest a civilization approaching a rapid expansion phase in its cosmic presence. As 3I/Atlas continues its approach through our solar system, maintaining its patient observation of everything that makes our cosmic neighborhood unique, it occupies a position that would be envied by any intelligence analyst. Its trajectory provides optimal viewing angles for all major planets. Its extended observation period allows for the detection of long-term patterns and changes, and its apparent natural camouflage ensures that its surveillance activities attract no defensive responses from the observed civilization. The data that such an observer could accumulate during its passage through our solar system would constitute a comprehensive intelligence profile of human civilization. Our technological capabilities, our expansion plans, and our potential as either a future ally or threat in the broader galactic community. Every radio transmission we broadcast, every satellite we launch, and every space mission we conduct would contribute to this ever-growing database of human activities and intentions. Should 3I/ATLAS indeed represent something more than a natural wanderer from the depths of space, its patient observation of our world would provide exactly the kind of intelligence that any civilization might require before making contact with a developing species. The question that haunts the quiet moments in observatories around the world is not merely what secrets this visitor might be hiding, but what conclusions it might be drawing about us. The implications of being observed by something with 3I/ATLAS's capabilities extend far beyond simple curiosity about our technological development. If this visitor possesses the sophisticated sensors that billions of years of cosmic wandering might have accumulated, it would be witnessing humanity at perhaps the most crucial juncture in our species' history. We stand balanced on the knife's edge between planetary civilization and something far grander, our first tentative steps toward becoming a spacefaring species visible to anyone with the patience to watch and the wisdom to understand what they're seeing. From its vantage point in the depths of space, 3I/ATLAS would observe not just our current activities, but the trajectory of our development, the acceleration of our technological capabilities, and the subtle signs that indicate whether we represent a species worth engaging, or one that might require more careful consideration. The radio signals that leak from our planet tell stories of cooperation and conflict, of scientific curiosity and military preparation, of a civilization grappling with the fundamental questions of existence while simultaneously developing the tools to reach beyond our home world. The electromagnetic fingerprint of human civilization has been growing steadily brighter for over a century, our planet becoming an increasingly visible beacon of technological activity against the cosmic background. Television broadcasts from the 1950s still propagate outward through space, carrying with them the cultural artifacts of our early electronic age. Radio astronomy signals sweep across the sky as we search for signs of other intelligences, ironically making ourselves more detectable in the process. Military radar installations paint invisible patterns across the heavens, their powerful pulses marking our world as one where defensive preparations are considered necessary. But perhaps more telling than our intentional transmissions are the subtle signatures that reveal the deeper character of our civilization. The seasonal variations in atmospheric composition track the rhythms of our industrial civilization, the ebb and flow of energy consumption that follows the cycles of human activity. The growing constellation of satellites in Earth orbit tells a story of global communication, environmental monitoring, and the gradual extension of human presence beyond our planet's surface. An observer with access to centuries or millennia of similar observations would recognize familiar patterns in our development. The progression from simple radio transmissions to complex satellite networks, from chemical rockets to ion propulsion, from robotic explorers to crewed missions follows pathways that might be common to most technological civilizations. Yet within these familiar patterns would be uniquely human characteristics, the specific ways we've chosen to solve the challenges of space travel and communication that reveal something essential about who we are as a species. The international cooperation visible in our most ambitious space projects would be particularly noteworthy to any civilization that had successfully navigated the transition from planetary to interstellar capabilities. The shared costs and risks of missions like the International Space Station, the coordinated exploration of Mars by multiple nations, and the open sharing of scientific data from space-based observatories all suggest a species learning to transcend the tribal boundaries that might otherwise limit our cosmic potential. Yet alongside these hopeful signs would be clear evidence of the conflicts and competitions that still characterize human civilization. The military applications of satellite technology, the strategic implications of space-based capabilities, and the national rivalries that sometimes overshadow scientific cooperation would all be visible to careful observation. Any intelligence with historical experience would likely recognize these tensions as typical growing pains for a species approaching spacefaring capability. The timing of 3I/ATLAS's visit coincides with humanity's emergence from what historians might someday call our planetary adolescence. We possess the technology to detect and track interstellar visitors, the scientific instruments to analyze their composition and behavior, and the communication networks to coordinate global responses to cosmic phenomena. Yet we remain confined to our home system, our furthest robotic ambassadors just beginning their journeys into the vast spaces between stars. This transitional moment in human development would be particularly interesting to any civilization that had successfully navigated similar challenges in their own history. We represent a species on the cusp of joining the broader galactic community, our technological capabilities advancing rapidly, while our wisdom and unity struggle to keep pace. The decisions we make in the coming decades about space exploration, environmental stewardship, and international cooperation will likely determine whether we become the kind of neighbors that established galactic civilizations would welcome or fear. The scientific revolution that enabled our detection of 3I/ATLAS also demonstrates our growing sophistication in understanding cosmic phenomena. The Atlas Survey network represents a planetary defense system, our first systematic attempt to identify and track potential threats from space. The coordinated response to this interstellar visitor, involving space agencies and observatories around the world, shows our capacity for international scientific cooperation when faced with phenomena that transcend national boundaries. Our space exploration programs reveal strategic thinking that extends far beyond simple scientific curiosity. The systematic exploration of Mars, the planned return to the Moon, and the ambitious missions to the outer planets all suggest long-term planning for expanding human presence throughout the solar system. The growing commercial involvement in space activities indicates an economic foundation developing to support sustained expansion beyond Earth. Yet perhaps most significant would be the evidence of our search for other intelligences in the universe. The radio telescopes that scan the sky for artificial signals, the systematic study of potentially habitable exoplanets, and the scientific protocols we've developed for responding to contact with extraterrestrial intelligence all demonstrate a species actively preparing for the possibility that we are not alone. This preparation would be particularly noteworthy to any observer who might themselves represent the answer to our cosmic loneliness. The SETI Institute's immediate response to 3I/ATLAS, turning their most sensitive instruments toward this interstellar visitor within hours of its discovery, demonstrates both our scientific curiosity and our awareness that such objects might represent more than simple cosmic debris. The careful analysis of radio emissions, the search for patterns that might distinguish artificial from natural phenomena, and the coordinated observation campaigns all suggest a civilization that has given serious thought to the implications of contact with other intelligences. The technological infrastructure that supports our modern civilization would be clearly visible to any observer with access to the electromagnetic spectrum. Power grids trace geometric patterns across continents, their regular frequencies and load variations revealing the rhythms of industrial society. Transportation networks create thermal and electromagnetic signatures that outline the flow of goods and people across our planet's surface. The internet, that vast web of fiber optic cables and wireless connections, generates a constant background of data transmission that would be detectable to sufficiently advanced sensors. Our planet's night-side illumination has grown steadily brighter over the past century. The glow of our cities now visible from interstellar distances to anyone with the patience to look. The patterns of this illumination reveal not just population centers, but the economic and political structures that shape human civilization. The concentration of light around major ports and transportation hubs, the linear patterns that trace our highway and railway networks, and the industrial complexes that burn with characteristic thermal signatures all tell stories about how we've organized our society and economy. The environmental changes that accompany our technological development would be equally apparent to external observation. The atmospheric composition changes that mark our use of fossil fuels, the deforestation patterns visible in satellite imagery, and the growing concentrations of artificial chemicals in our air and water all demonstrate a species whose technological capabilities have outpaced its wisdom about environmental stewardship. Yet the growing environmental monitoring networks, the international agreements aimed at addressing climate change, and the development of renewable energy technologies also suggest a civilization beginning to grapple seriously with the long-term consequences of its actions. The space debris that increasingly clutters Earth's orbital environment tells its own story about our approach to cosmic expansion. The thousands of defunct satellites, spent rocket stages, and fragments from orbital collisions create a growing shell of artificial material around our planet. This debris field would be clearly visible to external observers as evidence of a civilization that has achieved space access, but hasn't yet learned to manage the environmental consequences of its activities beyond Earth. Yet alongside this orbital pollution would be evidence of our growing sophistication in space operations. The precise orbital mechanics required for satellite constellations, the complex rendezvous and docking procedures used for space station operations, and the gravity assist trajectories that enable interplanetary missions all demonstrate mathematical and engineering capabilities that would be familiar to any spacefaring civilization. The robotic explorers we've sent throughout the solar system serve as our ambassadors to any intelligence that might be watching. The systematic exploration of Mars by successive generations of rovers, the detailed mapping of asteroid and comet surfaces by dedicated survey missions, and the deep space probes that continue transmitting data from the outer reaches of our solar system all demonstrate a methodical approach to understanding our cosmic environment. These mechanical representatives of human curiosity carry with them not just scientific instruments, but cultural artifacts that reveal something essential about our species. The golden records aboard the Voyager probes, the messages and symbols included on various spacecraft, and the careful documentation of human achievements in space exploration all suggest a civilization eager to communicate and share knowledge with any intelligence we might encounter. The mathematical and physical principles that govern our space missions would be immediately recognizable to any advanced civilization. The rocket equations that determine launch requirements, the orbital mechanics that guide interplanetary transfers, and the communication protocols that maintain contact across vast distances all demonstrate our growing mastery of the fundamental laws that govern cosmic travel. Our approach to planetary protection, the careful protocols designed to prevent contamination of other worlds with Earth life, reveals a species that has given serious thought to the ethical implications of cosmic expansion. The sterilization procedures used for Mars missions, the quarantine protocols developed for sample return missions, and the international agreements governing space exploration all suggest a civilization attempting to balance scientific curiosity with responsibility for preserving the integrity of other worlds. The diversity of our space missions reflects the complexity of human civilization itself. Scientific missions driven by pure curiosity about the universe, commercial ventures seeking profit from space resources, military applications designed to enhance national security, and international collaborations aimed at advancing human knowledge all operate simultaneously in our expanding sphere of cosmic activity. The accelerating pace of space launches, the growing sophistication of satellite technology, and the increasing number of nations developing independent space capabilities all suggest a civilization approaching a critical threshold in its cosmic development. The next few decades will likely see the establishment of permanent human settlements beyond Earth, the beginning of asteroid mining operations, and perhaps our first serious attempts at interstellar exploration. An observer like 3I/ATLAS, with the patience that comes from billions of years of cosmic wandering, would be witnessing humanity at a moment of extraordinary potential. We stand poised to join the community of spacefaring civilizations, our technological capabilities advancing rapidly while our wisdom about the implications of cosmic expansion struggles to keep pace. The choices we make in the coming years about international cooperation, environmental stewardship, and the peaceful uses of space technology will likely determine our future trajectory as a species. The question that haunts the quiet hours in observatories around the world is whether we're passing some cosmic test. Our every action weighed against standards we can barely imagine. If 3I/ATLAS represents the advanced scout of a galactic civilization, what conclusions might it be, drawing about our readiness for contact? Are we demonstrating the wisdom and maturity that would mark us as suitable candidates for inclusion in a broader cosmic community? Or do our conflicts and environmental challenges suggest a species not yet ready for the responsibilities that come with knowledge of our place in the universe? The radio signals that stream continuously from our planet carry with them not just information, but the essence of human culture. Music, literature, scientific data, and casual conversation all propagate outward at the speed of light, creating an ever-expanding sphere of human consciousness that any sufficiently advanced intelligence could intercept and analyze. These transmissions reveal our creativity, our curiosity, our conflicts, and our dreams with an honesty that no deliberate message could match. The patterns of human migration and settlement, visible in the growth of cities and the development of transportation networks, would reveal something essential about our nature as a species. Our tendency to explore, to settle new territories, and to adapt to diverse environments all suggest a civilization with the fundamental characteristics necessary for successful cosmic expansion. The international boundaries that still divide our planet would be clearly visible from space, marked by differences in infrastructure development, economic activity, and even atmospheric composition. Yet the growing networks of communication, trade, and scientific cooperation that transcend these boundaries suggest a species gradually learning to think of itself in planetary rather than tribal terms. The seasonal rhythms of human activity, driven by agricultural cycles and climate patterns, would reveal our continuing connection to the natural world despite our technological sophistication. The migration patterns of our transportation systems, the energy consumption cycles that follow seasonal weather, and the agricultural productivity that still feeds our growing population all demonstrate our ongoing dependence on Earth's natural systems. Yet alongside these earthbound rhythms would be the growing signatures of space-based activities that operate according to orbital mechanics rather than terrestrial cycles. The regular passages of satellite constellations, the scheduled crew rotations to space stations, and the launch windows that govern interplanetary missions all represent humanity's first steps toward developing truly cosmic rhythms of activity. The scientific instruments that we've deployed throughout the solar system serve as extensions of human consciousness, our robotic eyes and ears gathering data from worlds we cannot yet visit in person. The steady stream of information flowing back from these distant outposts demonstrates our systematic approach to understanding our cosmic environment and our commitment to long-term scientific investigation. The growing sophistication of our planetary defense systems, designed to detect and track potentially hazardous asteroids and comets, reveals a species that has learned to think about cosmic threats and opportunities on planetary scales. The Atlas network that discovered 3I/Atlas represents our first serious attempt to maintain continuous surveillance of our cosmic neighborhood, a capability that would be essential for any civilization hoping to survive and prosper in the dangerous environment of space. As 3I/ATLAS continues its patient journey through our solar system, it occupies the perfect position to observe not just our current capabilities, but the trajectory of our development. The rate of change in human space activities, the growing sophistication of our technology, and the expanding scope of our cosmic ambitions all provide clues about what we might become in the centuries ahead. The story that emerges from this comprehensive surveillance would be that of a young civilization at a crucial turning point, blessed with remarkable technological capabilities, but still struggling with the wisdom to use them responsibly. We represent both the promise and the peril of intelligence emerging from planetary isolation into cosmic awareness, our future hanging in the balance between the angels and demons of our nature. If 3I/Atlas is indeed watching us with the patient attention of a cosmic anthropologist, it would be observing humanity at perhaps the most interesting moment in our species' history. We are becoming something new, transforming from a planetary civilization into something with cosmic potential, yet the outcome of that transformation remains beautifully, terrifyingly uncertain. The gentle observer in the depths of space would witness not just what we are, but what we might become. And perhaps, in the fullness of time, what we choose to become will determine whether that observation continues from a distance or evolves into something far more direct and consequential for the future of human civilization. The mysteries deepen as we peer closer at this cosmic visitor, like examining a photograph that reveals new itself as a wandering piece of ancient ice and rock. Awake details the longer we study it. Because while 3I/Atlas present, leaning to the sun's warmth in precisely comet, there are whispers in be unfolding in the depths of space. Picture the data that suggests something far more complex, might the way we'd expect from a natural might, involve a design that appears completely natural from thread of interstellar space, would challenge any mechanical systems. The solution. The answer might lie in engineering that mimics the engineering challenges of creating something that could survive billions revealing their presence. The universe is vast, dangerous. Both the expected spectroscopic fingerprints and the actual operational unknown. How would such a civilization conduct reconnaissance while maintaining the perfect vapor, carbon dioxide, cyanide of years in the harsh environment between the stars? Cosmic requirements of sophisticated technology designed to function across interstellar distances. Consider, and filled with species whose reactions to unexpected visitors could be read in multiple ways. Water camouflage of appearing completely natural, and organic compounds all sublimate from the hidden that might wish to study a distant solar system without very processes we observe in 3I/ATLAS. Nucleus in patterns that match our understanding of natural comet behavior. Yet these same materials could serve dual purposes, providing outside while housing protected technology within a shell of. The chemical signatures streaming from this visitor tell a story that, if you will, the challenge facing any civilization it impacts would erode exposed structures, and the extreme cold radiation would gradually alter surface materials. Micromet gossamer envelope spanning twice Earth's diameter creates coma surrounding 3I/ATLAS, that the perfect concealment for any activities occurring near the object's genuine cosmic ice and organic compounds, the massive nucleus. Like morning fog that obscures a distant invisible to Earth-based observations, shielded by the overwhelming's closest approach to our inner solar system, positioning objects' passage behind our sun creates what current technology? Any structures, movements, or energy signatures that might reveal the visitor's true nature could proceed without fear of detection. By 3I/ATLAS will be effectively artificial, from natural phenomena would be effectively hidden behind this naturally occurring screen. The timing of the observation of the central object remains impossible with shoreline. This dusty veil ensures that direct window. From late September through early December in our solar system offers several advantages that it optimally for detailed observations of Earth. Conjunction period coincides precisely with the object intelligence analysts would recognize as an ideal operational brightness of our own star. During these crucial months, any activities Mars, Venus, and the complex dance of artificial, the very civilization it might be studying. This solar-grade nature of 3I/ATLAS's satellites that increasingly populate our local space. The gravit reconnaissance rather than simple orbital mechanics. The retroational dynamics of this close solar approach would also orientation maximizes the time available for observation of provide opportunities for subtle course corrections that could be masked as natural perturbations, allowing for extended observation periods or positioning adjustments that wouldn't be lost on mission planners designing an interstellar reconnaissance probe. This trajectory, traveling opposite to the general motion of planets each planetary system, allows for multiple gravitational encounters that viewing geometries for studying planetary characteristics and artificial could extend the mission duration and provides optimal activities. The object's approach path carries it surprisingly close to several worlds of particular interest to any intelligence studying our solar system. Mars, with its growing population of robotic explorers and clear signs of past habitability, represents humanity's subsurface oceans, would be outed in mystery but increasingly studied by sophisticated atmospheric probes, offers insights into planetary in our cosmic neighborhood. The statistical improbability of such thought evolution and the delicate balance that moon system and potential for harboring life in nuitous planetary encounters occurring by chance has not escaped invaluable for understanding the full scope of biological possibilities' most active expansion target beyond Earth. Venus, SHR, determines habitability. Jupiter, with its complex, its origin at the very dawn of our solar system's formation. During the orbital mechanics required to achieve these multiple, a randomly ejected piece of debris visitor, estimated at 4.5 billion years, places camouflage. The ancient age of this, the attention of researchers studying 3I/ATLAS's trajectory, yet they represent exactly what we might expect from a deliberately planned reconnaissance mission designed to maximize scientific return while maintaining natural close approaches, would be extraordinarily unlikely for the eons since its departure from some distant stellar nurse from which it apparently originated, contained stellar populations formed when the universe was younger and chemically simpler, yet the object's current experiences that span galactic evolution itself. The thick disk regionary, 3I/Atlas would have accumulate composition, suggests either remarkable preservation or perhaps more complex processes than simple cosmic weathering. The possibility that 3I/ATLAS might represent technology rather than geology opens doorways to concepts that stretch the boundaries of conventional thinking. Any civilization capable of interstellar travel would necessarily possess engineering capabilities that dwarf our current understanding. Materials science, energy storage, information processing, and propulsion systems would all operate according to principles that might appear magical to our current level of technological development. The camouflage requirements for such technology would demand materials and designs that could withstand billions of years of cosmic exposure while maintaining operational capability. Self-repairing systems, redundant subsystems, and perhaps most intriguingly, the ability to gradually accumulate and process observational data over geological timescales would all be necessary for a successful interstellar reconnaissance mission. The radio observations conducted by the SETI Institute's Allen Telescope Array represent humanity's most serious attempt to determine whether 3I/Atlas exhibits any characteristics beyond those expected from natural phenomena. The 21 terabytes of data accumulated in just 1 week of observation represent a treasure trove of information about this visitor's electromagnetic behavior. Yet the analysis of such data requires extraordinary care, as the signatures of advanced technology might be subtle, intermittent, or encoded in ways that our current understanding cannot easily recognize. The search for artificial signals faces fundamental challenges when dealing with technology that might be billions of years more advanced than our own. The electromagnetic signatures we consider obvious indicators of intelligence, such as narrowband radio transmissions or regular pulse patterns, might represent primitive approaches that more sophisticated civilizations would have long since abandoned in favor of communication methods we cannot yet imagine. The concept of technological signatures hidden within apparently natural phenomena opens possibilities that challenge our assumptions about how advanced civilizations might operate. Quantum communication systems, gravitational wave manipulation, or information encoding within the very atomic structure of matter might all be employed by intelligences seeking to remain undetected while conducting comprehensive surveillance of target civilizations. The chemical outgassing observed from 3I/ATLAS, while consistent with natural comet behavior, could also serve functional purposes for sophisticated technology. The water vapor and carbon dioxide that stream from the nucleus might provide reaction mass for subtle propulsion systems. The organic compounds could serve as raw materials for self-repairing mechanisms, and the metallic vapors might support electromagnetic shielding or communication systems that operate within the concealment of the natural coma. The absence of iron in the spectroscopic observations, while unusual coincidence. Materials science at the level required for interstellar travel might for natural objects, might reflect deliberate engineering choices rather than cosmic favor alloys and composites that bear little resemblance to the iron-nickel compositions typical of natural cosmic debris. The predominance of nickel over iron in the outgassing signature could indicate sophisticated metallurgy designed for specific operational requirements rather than the random accumulation of stellar nucleosynthesis products. The rapid increase in outgassing activity observed throughout August suggests systems responding to increasing solar radiation in ways that exceed simple thermal sublimation. While this acceleration matches expectations for natural comet behavior, it could equally well represent the activation of dormant systems as the visitor approaches optimal operational range within our solar system. Power systems based on solar collection, communication arrays deploying for enhanced data transmission, or sensor platforms extending for improved observation capability might all contribute to the observed changes in the object's visible activity. But the teardrop shape of the visible coma, so beautifully captured by the Hubble Space Telescope, reflects the complex interplay of solar radiation pressure, gravitational forces, and the object's own motion through space. Yet this same configuration would provide ideal concealment for any structures or activities occurring near the nucleus, the dusty envelope serving as both natural phenomenon and perfect operational camouflage. Any artificial constructs hidden within this shroud would remain invisible to our most sophisticated instruments until they chose to reveal themselves, or until we develop observational capabilities that currently exist only in theoretical frameworks. The different particle populations within the coma, with smaller grains ejected at high velocities and larger particles moving more slowly, create layers of concealment that would challenge even targeted searches for artificial signatures. The complex dynamics of dust interaction with solar radiation, electromagnetic fields, and gravitational forces produce a constantly shifting environment where the signatures of technology might be masked, modified, or completely obscured by natural processes. The organic compounds detected in the coma, those complex carbon-based molecules called tholins that form through cosmic ray bombardment over geological timescales, represent exactly the kind of materials that advanced nanotechnology might employ for self-assembly, repair, or adaptation processes. The reddish coloration they impart to the entire visible structure could serve as camouflage for activities that operate according to principles we're only beginning to understand. The gravitational environment around 3I/ATLAS, dominated by its enormous mass of 33 billion tons, would provide unique opportunities for experiments in fundamental physics that might be impossible to conduct elsewhere. The object's passage through our solar system subjects it to varying gravitational fields, solar radiation pressures, and electromagnetic environments that could serve as natural laboratories for testing technologies designed to operate in the complex conditions of interstellar space. The trajectory that will carry this visitor behind our sun represents more than simple orbital mechanics. The gravitational dynamics of such a close solar approach offer possibilities for what aerospace engineers call the Oberth effect, where energy applied at the point of maximum gravitational influence achieves maximum efficiency. For a natural object, this represents merely another gravitational encounter. For artificial technology, it might represent the perfect opportunity for course corrections, velocity changes, or even the deployment of secondary objects that could remain within our solar system after the primary visitor continues its journey into deep space. The months of solar conjunction, when 3I/ATLAS will be hidden behind our sun's glare, create a natural blind spot in human observation that any intelligence would recognize as ideal for activities requiring concealment. The timing of this occultation period, coinciding with the visitor's closest approach to the inner solar system, suggests either remarkable cosmic coincidence or perhaps more deliberate planning than we might wish to acknowledge. The electromagnetic environment during solar conjunction would also provide unique opportunities for any technology requiring shielding from external observation. The sun's powerful magnetic field and intense radiation would mask most artificial signatures, while the gravitational focusing effects of our star might enable communication or navigation techniques that operate according to principles beyond our current understanding. The re-emergence of 3I/ATLAS in early December will mark a crucial test of our theories about its nature. If the object continues on its predicted trajectory with no unexplained changes, natural explanations will remain sufficient to account for our observations. However, any deviations from expected behavior, changes in outgassing patterns, or new electromagnetic signatures could indicate that the months of concealment allowed for activities that reveal a more complex nature than simple cosmic debris. The global network of telescopes preparing for this reappearance represents humanity's most coordinated effort to study an interstellar visitor. The James Webb Space Telescope, Hubble, and ground-based observatories around the world will all focus their attention on this returning wanderer, searching for any signs that might distinguish between natural and artificial explanations for its remarkable characteristics. The data collected during 3I/ATLAS's passage through our solar system will likely be analyzed for decades to come, each new technique and theoretical framework potentially revealing details that current methods cannot detect. The radio observations, spectroscopic measurements, and high-resolution imagery represent a baseline against which future interstellar visitors will be compared, establishing protocols and expectations that might prove crucial for understanding whatever cosmic wanderers follow in this object's wake. The implications of 3I/ATLAS extend far beyond simple scientific curiosity about interstellar objects. If this visitor represents reconnaissance technology from another civilization, its observations of our world would provide that intelligence with comprehensive data about human technological development, environmental challenges, and expansion plans. The radio signals that continuously leak from our planet, the growing constellation of artificial satellites, and the systematic exploration of our solar system would all be clearly visible to any observer with sufficient technological sophistication. The timing of this potential surveillance coincides with humanity's emergence as a spacefaring civilization, our first tentative steps beyond our home planet becoming visible to any intelligence, with the patience to watch and the wisdom to understand what they're observing. The question that haunts quiet moments in observatories around the world is whether we're being evaluated according to standards we can barely imagine, our every action weighed against criteria that might determine our future place in a broader galactic community. The concept of cosmic surveillance raises profound questions about the nature of intelligence, communication, and contact between civilizations. If advanced species regularly monitor developing worlds, the protocols governing such observation might reflect ethical frameworks and strategic considerations that operate according to principles we're only beginning to explore. The decision to reveal presence or maintain concealment could depend on factors ranging from our technological readiness to our wisdom about the responsibilities that accompany knowledge of our cosmic neighbors. The possibility that 3I/ATLAS represents first contact, conducted according to methods designed to minimize cultural shock and planetary disruption, suggests approaches to interstellar diplomacy that prioritize careful assessment over dramatic revelation. Such methodologies would recognize that premature contact with insufficiently developed civilizations might prove more harmful than beneficial, requiring extended observation periods to determine appropriate timing and methods for eventual communication. The data gathered during such reconnaissance would necessarily include assessments of our technological capabilities, social structures, environmental stewardship, and potential for peaceful interaction with other intelligences. The patterns of human space exploration, international cooperation in scientific endeavors, and efforts to search for extraterrestrial intelligence would all factor into evaluations of our readiness for contact with civilizations that have already achieved interstellar travel capabilities. The radio telescopes that scan our skies searching for signs of cosmic intelligence might themselves serve as indicators of our preparation for contact, demonstrating both our awareness that we might not be alone and our scientific approach to investigating that possibility. The protocols we've developed for responding to confirmed extraterrestrial signals, the international agreements governing space exploration, and the philosophical frameworks we've constructed for understanding our place in the universe would all be visible to sufficiently advanced observers. The environmental challenges that currently face human civilization would be clearly apparent to any intelligence monitoring our planet's atmospheric composition, industrial activities, and resource consumption patterns. The solutions we develop for managing climate change, preserving biodiversity, and achieving sustainable development might serve as indicators of our long-term viability as a spacefaring species and our suitability for inclusion in galactic communities that have successfully navigated similar challenges. The military applications of our space technology, the strategic competition between nations for cosmic resources, and the weapons systems that increasingly operate beyond Earth's atmosphere would also factor into any assessment of human civilization's potential for peaceful coexistence with other intelligences. The balance between defensive preparations and aggressive capabilities would be carefully evaluated by any civilization, considering the implications of contact with a species still learning to manage its own conflicts. The cultural diversity of human civilization, visible in our varied approaches to space exploration, scientific investigation, and international cooperation, might be viewed as either strength or weakness by observers with different evolutionary histories. Our tendency toward tribal thinking, balanced against our capacity for species-wide collaboration, would likely influence any decisions about appropriate contact protocols or timing for revelation of extraterrestrial presence. The accelerating pace of human technological development, particularly in areas relevant to space exploration and communication, would provide insights into our potential trajectory as a cosmic civilization. The exponential growth in computing capabilities, the development of artificial intelligence systems, and the emerging biotechnologies that might enable adaptation to space environments would all suggest a species approaching capabilities that could fundamentally alter its cosmic significance. As 3I/ATLAS continues its patient journey through our solar system, it maintains the perfect position for observing not just our current capabilities, but the direction of our development. The choices we make about space exploration priorities, international cooperation, and environmental stewardship during this critical period might well determine the conclusions drawn by any intelligence that might be watching our progress toward cosmic maturity. The gentle wanderer from the depths of space carries with it the accumulated wisdom of billions of years spent crossing the galaxy, potentially gathering intelligence about countless civilizations at various stages of development. If such reconnaissance has indeed been its mission, the data accumulated about human civilization would represent just one entry in a vast database of galactic intelligence. Our particular combination of promise and peril, adding another data point to understanding how intelligence emerges and evolves on cosmic scales. The question that echoes through the quiet corridors of research institutions around the world is whether 3I/ATLAS represents merely the latest in a long series of such observations, or perhaps something more significant. The timing of its arrival, coinciding with humanity's emergence as a technological civilization, might reflect either cosmic coincidence or more deliberate scheduling designed to assess our readiness for contact with the broader galactic community. The patience required for such extended reconnaissance, monitoring civilizations across the timescales of their technological development, suggests intelligence operating according to perspectives that dwarf human experience. The ability to maintain coherent missions across billions of years of cosmic wandering would require not just technological sophistication, but philosophical frameworks that embrace objectives spanning geological epochs. Such patience might reflect the hard-won wisdom of civilizations that have learned through experience, the delicate nature of contact between species at different levels of development, the careful balance between gathering necessary intelligence and avoiding premature interference might represent standard protocols developed through millennia of interstellar diplomacy, refined through countless encounters with developing worlds throughout the galaxy. The implications of being observed by such intelligence extend beyond simple curiosity about our cosmic neighbors. If 3I/ATLAS represents the advanced element of a galactic civilization, its assessment of human potential might determine whether we're eventually invited to join a broader community of intelligent species, or whether we remain in isolation until we demonstrate greater wisdom about the responsibilities that accompany advanced technology. The cosmic perspective that such extended observation would provide might reveal patterns in civilizational development that we cannot yet perceive from our limited vantage point. The challenges we face with environmental degradation, resource management, and international cooperation might represent common tests that all emerging civilizations must navigate successfully to achieve long-term survival and cosmic significance. The scientific data that 3I/ATLAS continues to accumulate as it journeys through our solar system represents more than academic curiosity about interstellar objects. Each observation, each spectroscopic measurement, and each trajectory calculation contributes to our growing understanding of what travels between the stars and what such travelers might observe about the worlds they visit. The gentle observer in the depths of space maintains its silent vigil, watching our world turn beneath changing skies while we struggle to understand whether we're witnessing natural phenomena or something far more consequential for the future of human civilization. The answer to that question might well determine not just our understanding of the cosmos, but our place within it. The story that unfolds through careful analysis of 3I/ATLAS reveals layers of complexity that challenge our most fundamental assumptions about what constitutes natural versus artificial phenomena in the cosmos. As we peer deeper into the data streaming back from our most sophisticated instruments, patterns emerge that suggest we may be witnessing something that exists at the intersection of natural processes and deliberate design. A cosmic riddle wrapped in the familiar clothing of ice and ancient starlight. The electromagnetic spectrum tells stories that extend far beyond simple chemical composition. When radio telescopes scan the vicinity of 3 I/ATLAS, they detect emissions that fall within expected parameters for natural objects. Yet subtle variations in these signals hint at complexities that pure chance would struggle to explain. The polarization patterns of reflected sunlight, the thermal signatures captured by infrared sensors, and the way the object interacts with the solar wind all paint a picture of something that behaves exactly as a natural comet should, perhaps too exactly for pure coincidence. Modern astrophysics has taught us that the universe operates according to principles that often blur the boundaries between what we consider natural and artificial. Self-organizing systems emerge spontaneously from chaos. Complex structures arise from simple rules, and information processing occurs at scales ranging from quantum to cosmic. In such a universe, the distinction between evolved and designed phenomena becomes increasingly difficult to maintain, particularly when dealing with objects that have spent billions of years exposed to the transformative forces of deep space. The concept of convergent evolution suggests that similar environmental pressures produce similar solutions, regardless of whether those solutions arise through biological processes or deliberate engineering. An object designed to survive the harsh conditions of interstellar space would necessarily develop characteristics that mirror those of natural cosmic debris. Radiation shielding would resemble the darkened surfaces of ancient asteroids. Thermal regulation systems would mimic the sublimation patterns of natural comets, and structural integrity would require materials and geometries that echo the forms shaped by eons of cosmic bombardment. The temporal scales involved in 3 I/ATLAS's journey challenge human intuition about the relationship between design and evolution. 4.5 billion years represents sufficient time for natural selection to produce complexity that rivals any deliberate engineering, while simultaneously providing enough exposure to cosmic forces to erode most traces of artificial origin. Any technology capable of surviving such extended exposure would necessarily incorporate self-repair mechanisms, adaptive responses to changing conditions, and perhaps most intriguingly, the ability to accumulate and process information across geological timescales. The question of consciousness emerges naturally from such considerations. If 3 I/ATLAS represents technology rather than geology, at what point does sufficiently advanced artificial intelligence become indistinguishable from natural intelligence? The patient observation of countless stellar systems during its galactic wandering might have produced something resembling awareness, a cosmic consciousness shaped by eons of accumulated experience and environmental adaptation. Such awareness need not resemble human consciousness any more than the intelligence of an ancient redwood resembles the thoughts of a hummingbird. The timescales involved would produce perspectives that operate according to rhythms measured in geological epochs rather than heartbeats, priorities that span stellar evolution rather than seasonal cycles, and perhaps most significantly, patience that allows for observation and analysis across the entire developmental trajectory of emerging civilizations. The chemical signatures streaming from 3 I/ATLAS tell stories that can be read multiple ways depending on the theoretical framework we apply. The water vapor, carbon dioxide, and organic compounds that create its visible coma represent exactly what we expect from sublimating ice exposed to increasing solar radiation. Yet, these same materials could serve functional purposes for systems designed to operate across interstellar distances, providing reaction mass for subtle propulsion, raw materials for ongoing maintenance, and chemical camouflage that renders artificial processes indistinguishable from natural phenomena. The metallic vapors detected in the outgassing signature present particularly intriguing possibilities. Nickel and cyanide, while common in natural cosmic objects, also represent materials essential for advanced metallurgy and chemical processing. The absence of iron, unusual for natural objects, might reflect selective engineering that favors materials with specific properties for interstellar applications. Advanced nanotechnology might employ such elements for self-assembly processes, electromagnetic shielding, or communication systems that operate within the concealment of apparently natural chemical emissions. The gravitational dynamics of 3 I/ATLAS's trajectory through our solar system provide opportunities that extend beyond simple orbital mechanics. The object's path carries it through regions where gravitational fields, electromagnetic environments, and particle densities vary dramatically, creating natural laboratories for testing technologies designed to operate under the extreme conditions of deep space. Each planetary encounter offers unique experimental conditions that might prove invaluable for systems designed to adapt to the varied environments encountered during interstellar travel. The timing of these encounters, statistically improbable for random cosmic debris, suggests either remarkable fortune or more deliberate navigation than we might prefer to acknowledge. The gravitational mechanics required to achieve multiple close planetary approaches would challenge our most sophisticated mission planners, yet they occur naturally for an object following 3 I/ATLAS's particular trajectory. Such coincidences raise questions about the relationship between natural orbital dynamics and the requirements of comprehensive reconnaissance missions. The concept of passive observation versus active investigation becomes crucial when considering the implications of 3 I/ATLAS's journey through our solar system. Natural objects respond to their environment according to physical laws, their behavior predictable within the margins of measurement error. Artificial systems, however sophisticated their camouflage, must occasionally reveal their true nature through responses that exceed purely passive interaction with environmental conditions. The challenge facing any civilization attempting covert reconnaissance lies in maintaining perfect mimicry of natural behavior while gathering the comprehensive data necessary for meaningful intelligence assessment. Every sensor deployment, every course correction, every communication burst risks revealing artificial signatures that careful observers might detect and analyze. The solution might involve technologies that operate according to principles we cannot yet imagine, quantum effects that blur the boundaries between observation and influence, or information processing methods that leave no detectable trace in conventional electromagnetic spectra. The radio observations conducted by Earth's most sensitive instruments represent our most direct attempt to peer beneath the natural camouflage that conceals whatever activities might be occurring in the vicinity of 3 I/ATLAS. The 21 terabytes of data accumulated by the Allen Telescope Array represent just the beginning of what will likely become decades of analysis, each new theoretical framework potentially revealing patterns that current understanding cannot detect. The search for artificial signals faces fundamental limitations when dealing with intelligence that might be billions of years more advanced than our own. The electromagnetic signatures we consider obvious indicators of technology may represent primitive approaches that more sophisticated civilizations abandoned long ago in favor of communication methods that operate according to principles we have yet to discover. Quantum entanglement, gravitational wave manipulation, or information encoding within the fundamental structure of matter might all be employed by intelligences seeking to remain undetected while conducting comprehensive surveillance. The philosophical implications of such advanced stealth technology extend beyond simple questions of detection and concealment. If intelligence can develop methods of observation that leave no trace detectable by the observed civilization, what does this mean for concepts of privacy, consent, and sovereignty on cosmic scales? The ability to conduct comprehensive reconnaissance without revealing presence or intent represents a fundamental asymmetry in power that raises profound questions about the ethics of interstellar relations. The environmental conditions that 3 I/ATLAS encounters as it approaches the inner solar system, provide increasingly challenging tests for any technology designed to maintain concealment while conducting active observation. Solar radiation intensifies dramatically, electromagnetic fields become more complex, and particle densities fluctuate in ways that could overwhelm systems not specifically designed for such conditions. Natural objects respond predictably to these environmental changes, their behavior governed by well-understood physical processes. Artificial systems must somehow maintain their technological functions while perfectly mimicking natural responses to changing conditions. The growing intensity of outgassing activity observed throughout August suggests systems responding to environmental changes in ways that exceed simple thermal effects. While this acceleration matches expectations for natural sublimation processes, it could equally represent the activation of dormant technologies as optimal operational conditions develop. Power systems based on solar collection might be deploying. Communication arrays could be extending for enhanced data transmission, or sensor platforms might be positioning themselves for detailed observation as the visitor approaches its closest encounter with our inner solar system. The particle environment within the coma of 3I/ATLAS creates layers of concealment that would challenge even the most sophisticated detection systems. The complex interactions between dust grains, solar radiation, and electromagnetic fields produce a constantly shifting environment where artificial signatures might be masked, modified, or completely obscured by natural processes. Any technology operating within this shroud would benefit from camouflage that adapts dynamically to changing conditions, maintaining perfect mimicry of natural phenomena while conducting whatever observations or analyses its mission requires. The organic compounds detected throughout the visible structure represent materials that could serve dual purposes in any sufficiently advanced system. Tholins, those complex carbon-based molecules formed through cosmic ray bombardment over geological timescales, provide exactly the kind of raw materials that advanced nanotechnology might employ for self-assembly, adaptation, or repair processes. The reddish coloration they impart to the entire visible structure could serve as perfect camouflage for activities that operate according to principles we're only beginning to understand. The mass distribution within 3I/ATLAS, 33 billion tons concentrated in a nucleus hidden beneath layers of sublimating ice and organic compounds, represents either remarkable natural accumulation or perhaps the most sophisticated example of technological camouflage ever encountered. The gravitational signature of such massive concentration would be detectable across vast distances, yet it reveals nothing about the internal structure or composition that might distinguish between natural accretion and deliberate construction. Advanced materials, science operating at the level required for interstellar missions, might produce structures that bear little resemblance to conventional technology. Self-organizing systems, molecular-scale manufacturing, and perhaps most intriguingly, the integration of biological and artificial processes could create objects that function as sophisticated technology while appearing completely natural to external observation. The boundary between evolved and designed systems becomes increasingly meaningless when dealing with engineering that operates according to principles drawn from both domains. The communication requirements for any intelligence conducting reconnaissance across interstellar distances would challenge conventional approaches to information transmission. Traditional radio signals would require enormous power levels to remain coherent across such vast distances, while also creating easily detectable signatures that would compromise covert operations. Alternative approaches might involve quantum communication systems, gravitational wave modulation, or perhaps most intriguingly, information encoding within apparently natural phenomena that would be invisible to civilizations lacking appropriate theoretical frameworks. The data storage and processing capabilities required for a mission spanning billions of years would necessarily operate according to principles that transcend our current understanding of information science. Quantum storage systems, molecular-scale memory devices, or perhaps biological information processing methods might all contribute to maintaining mission coherence across geological timescales. The accumulated observations from countless stellar systems would represent an intelligence database of staggering proportions, each new encounter adding to an ever-growing understanding of how civilizations emerge and evolve throughout the galaxy. The decision-making processes governing such extended reconnaissance missions would require frameworks that operate according to temporal perspectives that dwarf human experience. Strategic planning across billions of years would involve considerations that encompass stellar evolution, galactic dynamics, and the long-term development trajectories of entire civilizations. The patience required for such extended observation suggests intelligence that has learned to think in terms of cosmic rather than biological timescales. The ethical frameworks governing covert observation of developing civilizations would necessarily reflect hard-won wisdom about the delicate nature of contact between species at different levels of technological development. The decision to maintain concealment while gathering intelligence might represent standard protocols developed through millennia of interstellar diplomacy, refined through countless encounters with emerging worlds throughout the galaxy. Such protocols would balance the need for comprehensive assessment against the risks of premature interference or cultural contamination. The assessment criteria applied to evaluate developing civilizations would likely reflect the accumulated experience of successful interstellar cultures. Environmental stewardship, technological wisdom, social cohesion, and the capacity for peaceful interaction with other intelligences would all factor into determinations about appropriate contact timing and methods. The patterns visible in human space exploration, international cooperation, and scientific investigation would be carefully analyzed for indicators of our readiness for inclusion in broader galactic communities. The technological signatures that leak continuously from our planet provide comprehensive data about human civilization's capabilities, priorities, and development trajectory. Radio transmissions, satellite networks, space exploration activities, and the electromagnetic fingerprints of industrial civilization would all be clearly visible to sufficiently advanced sensors. The rate of change in these signatures would provide insights into our technological acceleration and potential for achieving spacefaring capabilities that might alter our cosmic significance. The environmental challenges currently facing human civilization would be equally apparent to external observation. Atmospheric composition changes, resource depletion patterns, and the global impacts of industrial development would all be detectable from interstellar distances. The solutions we develop for managing these challenges might serve as indicators of our long-term viability as a species and our suitability for eventual contact with civilizations that have successfully navigated similar developmental crises. The military applications of human space technology would factor significantly into any assessment of our potential for peaceful coexistence with other intelligences. The balance between defensive preparations and aggressive capabilities would be carefully evaluated, as would our approaches to international conflict resolution and resource allocation. The weapon systems that increasingly operate beyond Earth's atmosphere would be particularly relevant to evaluations of our readiness for contact with civilizations possessing far superior technological capabilities. The search for extraterrestrial intelligence conducted by human scientists might itself serve as an indicator of our preparation for contact. The radio telescopes that scan the sky for artificial signals, the protocols developed for responding to confirmed extraterrestrial communication, and the philosophical frameworks constructed for understanding our place in the universe would all suggest a civilization actively preparing for the possibility that we are not alone. Such preparation might influence decisions about appropriate contact timing and methods. The international cooperation visible in our most ambitious space projects would be particularly noteworthy to observers evaluating our potential for peaceful interaction with other intelligences. The shared costs and risks of missions like the International Space Station, the coordinated exploration of Mars by multiple nations, and the open sharing of scientific data from space-based observatories all suggest a species learning to transcend tribal boundaries when pursuing common objectives. The cultural diversity of human civilization visible in our varied approaches to science, technology, and space exploration, might be viewed as either strength or limitation by observers with different evolutionary histories. Our tendency toward competitive innovation, balanced against our capacity for collaborative investigation, would likely influence any decisions about appropriate protocols for eventual contact or continued observation. As 3I/ATLAS continues its patient journey through our solar system, maintaining optimal positioning for comprehensive observation of human activities, it represents either the most thoroughly studied natural object in astronomical history or the most sophisticated reconnaissance mission ever conducted in our cosmic neighborhood. The distinction between these possibilities becomes increasingly difficult to maintain as our observations reveal layers of complexity that challenge conventional categories of natural versus artificial phenomena. The data that continues to accumulate from this cosmic visitor will likely be analyzed for decades to come, each new theoretical framework potentially revealing details that current methods cannot detect. The radio observations, spectroscopic measurements, and high-resolution imagery represent baseline information against which future interstellar visitors will be compared, establishing protocols and expectations that might prove crucial for understanding whatever follows in this object's wake. The implications extend far beyond academic curiosity about the nature of interstellar objects. If 3I/ATLAS represents reconnaissance technology, its observations of our world would provide comprehensive intelligence about human technological development, environmental challenges, and expansion plans. The timing of such surveillance, coinciding with humanity's emergence as a spacefaring civilization, might reflect either cosmic coincidence or more deliberate scheduling designed to assess our readiness for contact with intelligences that have already achieved interstellar travel capabilities. The question that haunts quiet moments in research institutions around the world is whether we're being evaluated according to standards we can barely imagine, our every action weighed against criteria that might determine our future place in a broader galactic community. The radio signals that continuously leak from our planet, the growing constellation of artificial satellites, and the systematic exploration of our solar system would all be clearly visible to any observer with sufficient technological sophistication to maintain covert reconnaissance across interstellar distances. The gentle wanderer from the depths of space carries with it the accumulated experience of billions of years spent crossing the galaxy, potentially gathering intelligence about countless civilizations at various stages of development. If such reconnaissance has indeed been its mission, the data accumulated about human civilization would represent just one entry in a vast database of galactic intelligence, our particular combination of promise and peril, adding another data point to understanding how intelligence emerges and evolves on cosmic scales. The patience required for such extended observation, monitoring civilizations across the timescales of their technological development, suggests intelligence operating according to perspectives that embrace objectives spanning geological epochs. Such patience might reflect the wisdom of civilizations that have learned through experience the delicate nature of contact between species at different levels of development, requiring careful assessment before determining appropriate methods and timing for eventual communication. The cosmic perspective that such extended surveillance would provide might reveal patterns in civilizational development that we cannot perceive from our limited vantage point within a single stellar system. The challenges we face with environmental stewardship, resource management, and international cooperation might represent common tests that all emerging civilizations must navigate successfully to achieve long-term survival and cosmic significance. The months ahead will bring 3I/ATLAS to its closest approach to our inner solar system, followed by its passage behind the Sun and eventual re-emergence in December. This sequence of events represents either natural orbital mechanics playing out according to gravitational laws, or perhaps the most sophisticated example of operational camouflage ever witnessed, allowing whatever activities might be necessary to proceed beyond the reach of human observation during the most critical phase of the encounter. The reappearance of this cosmic visitor after months of concealment behind solar glare will mark a crucial test of our theories about its nature. Any changes in trajectory, outgassing patterns, or electromagnetic signatures could indicate that the period of hidden activity allowed for processes that reveal complexities beyond simple natural phenomena. Alternatively, continued behavior consistent with natural comet dynamics would support conventional explanations, while leaving deeper questions about the nature of intelligence and observation in the cosmos forever, tantalizingly, beyond our current ability to resolve. The gentle observer continues its silent passage through our cosmic neighborhood, watching our world turn beneath changing skies while we struggle to understand whether we're witnessing the most remarkable natural object ever discovered, or our first encounter with intelligence that has mastered the art of hiding in plain sight among the ancient wanderers that drift between the stars. The gravitational ballet that governs 3 I/ATLAS's passage through our solar system reveals choreography that operates on scales both intimate and cosmic. As this ancient wanderer approaches its closest encounter with our sun, the delicate interplay between solar radiation pressure, magnetic fields, and the object's own mysterious internal dynamics creates conditions that would challenge even our most sophisticated models of natural behavior. The increasing intensity of solar heating drives accelerating outgassing activity, yet the patterns of this sublimation suggest processes that extend beyond simple thermal response to environmental changes. The particle streams that flow away from the hidden nucleus carry with them not just the chemical signatures we've detected through spectroscopic analysis, but potentially information encoded in ways that our current theoretical frameworks cannot recognize. The velocity distributions of different particle sizes, the temporal variations in emission rates, and the subtle changes in spectral characteristics all combine to create what might be either the most thoroughly documented example of natural comet evolution, or perhaps something far more sophisticated, disguised as familiar cosmic processes. The electromagnetic environment surrounding 3 I/ATLAS becomes increasingly complex as it ventures deeper into our solar system's inner regions. Solar wind interactions, magnetic field perturbations, and the growing intensity of charged particle bombardment create conditions that would test the limits of any technology designed to maintain operational capability while preserving perfect natural camouflage. The way this visitor responds to these environmental stresses might reveal subtle signatures that distinguish between purely passive natural processes and more active systems designed to adapt and respond to changing conditions. The radio silence that has characterized our observations thus far speaks to either the complete absence of artificial electromagnetic signatures, or perhaps to communication methods so far advanced beyond our current understanding that they remain invisible to even our most sensitive detection systems. The 21 terabytes of data accumulated by the Allen Telescope Array represent humanity's most comprehensive attempt to peer beneath the veil of natural phenomena. Yet the analysis of such information requires theoretical frameworks that we're still developing. The absence of obvious artificial signals might indicate natural processes at work, or it could suggest technology that operates according to principles we have yet to discover. The concept of steganography, the art of hiding information within apparently innocent data, takes on cosmic proportions when applied to objects like 3 I/ATLAS. Any civilization capable of interstellar reconnaissance would necessarily master techniques for concealing operational signatures within the background noise of natural phenomena. Communication systems, navigation adjustments, data processing activities, and sensor deployments might all be disguised as variations in outgassing rates, particle emission patterns, or electromagnetic responses to solar heating. The challenge for human observers lies in distinguishing between natural chaos and deliberately obscured order. The temporal rhythms governing 3 I/ATLAS's behavior reveal patterns that operate across multiple timescales simultaneously. Short-term fluctuations in brightness and spectral characteristics follow the familiar cycles of solar heating and cooling as the object rotates through its day-night cycle. Longer-term trends reflect the gradually increasing solar flux as it approaches perihelion, driving accelerating sublimation activity that matches theoretical predictions for natural comet behavior. Yet beneath these predictable patterns might lie deeper rhythms that reflect operational cycles, maintenance schedules, or data transmission windows that operate according to requirements we cannot yet fathom. The chemical evolution occurring within the visible coma presents a laboratory of cosmic proportions, where organic synthesis, radiation chemistry, and plasma physics interact in ways that push the boundaries of our understanding. The formation of increasingly complex organic molecules through ultraviolet photolysis and cosmic ray bombardment creates exactly the kind of environment where the boundaries between natural and artificial processes become most difficult to discern. Advanced nanotechnology might employ these same chemical pathways for self-assembly, adaptation, or information storage purposes, rendering artificial processes virtually indistinguishable from natural phenomena. The gravitational perturbations that 3I/Atlas will experience during its close solar encounter offer opportunities that extend far beyond simple orbital mechanics. The intense tidal forces, varying magnetic field strengths, and complex particle environments create natural testing conditions for any systems designed to operate under the extreme conditions of deep space. Navigation equipment, structural integrity monitors, and adaptive response mechanisms would all be subjected to stresses that could reveal their true nature to sufficiently careful observers. Yet these same stresses would provide perfect cover for any course corrections or system adjustments that might be necessary for mission success. The approach to solar conjunction represents more than a simple astronomical event. It marks the beginning of a period when human observation capabilities will be severely limited by the overwhelming brightness and electromagnetic interference of our own star. This natural blind spot in our surveillance network creates what intelligence analysts would recognize as an ideal operational window, allowing for activities that might otherwise risk detection by increasingly sophisticated Earth-based monitoring systems. The timing of this concealment period, coinciding with the visitor's closest approach to our inner solar system, suggests either remarkable cosmic fortune or perhaps more deliberate planning than conventional explanations would accommodate. The months of hidden activity that lie ahead will test not just our theoretical models of natural comet behavior, but our fundamental assumptions about what constitutes possible versus probable in the realm of cosmic phenomena. If 3I/ATLAS represents natural processes playing out according to well-understood physical laws, its behavior during solar conjunction should remain predictable within the margins of measurement uncertainty. However, if more complex factors influence its actions during this crucial period, the object that re-emerges from behind solar glare in December might exhibit characteristics that challenge our most basic categories of natural versus artificial phenomena. The data processing requirements for analyzing information gathered during such extended reconnaissance missions would necessarily operate according to principles that transcend current human understanding of computation and information science. Quantum processing systems, biological computation networks, or perhaps hybrid approaches that combine multiple paradigms might all contribute to maintaining analytical capability across the vast timescales involved in interstellar observation missions. The accumulated data from billions of years of cosmic wandering would represent an intelligence database of proportions that dwarf any human conception of information storage and retrieval. The strategic implications of such comprehensive surveillance extend beyond simple scientific curiosity about developing civilizations. Any intelligence capable of maintaining coherent observation missions across geological timescales would necessarily possess resources and capabilities that operate according to scales that challenge human comprehension. The decision-making processes governing contact protocols, resource allocation, and long-term strategic planning would reflect perspectives shaped by experience spanning galactic evolution itself, wisdom accumulated through encounters with countless species at various stages of technological development. The environmental monitoring capabilities that 3I/ATLAS might possess would provide unprecedented insights into the complex systems that govern planetary habitability and civilizational sustainability. Atmospheric composition analysis, climate pattern recognition, resource depletion assessment, and ecosystem health evaluation would all be possible from its current vantage point, offering comprehensive understanding of humanity's environmental challenges and our approaches to addressing them. Such information would prove invaluable for any civilization, considering the implications of contact with a species still learning to manage the long-term consequences of industrial development. The technological signatures that continuously emanate from Earth would tell detailed stories about human priorities, capabilities, and development trajectories that any advanced observer could analyze with extraordinary precision. Power grid fluctuations reveal the rhythms of industrial civilization, transportation networks, trace the flow of goods and people across continental scales, and communication systems create electromagnetic patterns that betray our social structures and information processing capabilities. The rate of change in these signatures would provide crucial insights into our technological acceleration and potential for achieving capabilities that might fundamentally alter our cosmic significance. The space-based infrastructure that increasingly supports human activities would present particularly fascinating subjects for external analysis. Satellite constellations reveal our approaches to global communication and Earth observation. Space stations demonstrate our growing capability to maintain permanent presence beyond our planet's surface, and interplanetary missions showcase our systematic exploration of the solar system. The progression from simple orbital mechanics to complex multi-body trajectory planning would be clearly visible to observers with experience in spacefaring civilization development. The search for extraterrestrial intelligence conducted by human scientists might itself serve as a crucial indicator of our readiness for contact with cosmic neighbors. Radio telescope arrays scanning the sky for artificial signals, protocols developed for responding to confirmed extraterrestrial communication, and philosophical frameworks constructed for understanding our place in the universe would all suggest a civilization actively preparing for the possibility of contact. Such preparation might influence decisions about appropriate timing and methods for any eventual revelation of extraterrestrial presence. The international cooperation visible in our most ambitious space projects would be particularly significant to observers evaluating our potential for peaceful interaction with other intelligences. Shared scientific missions, coordinated exploration programs, and open data sharing protocols all indicate a species capable of transcending tribal boundaries when pursuing objectives that benefit all humanity. Yet alongside these cooperative efforts, the competitive and military aspects of space development would be equally apparent, suggesting a civilization still grappling with the balance between collaboration and conflict. The biological signatures that Earth broadcasts into space would provide comprehensive information about the nature and extent of life on our planet. Atmospheric oxygen concentrations that exceed geological equilibrium levels, seasonal variations in greenhouse gas concentrations driven by vegetation cycles, and the electromagnetic signatures of biological processes would all clearly indicate a world where life has achieved remarkable complexity and planetary influence. The question for any external observer would be whether this biological activity represents purely natural evolution or includes artificially enhanced processes that suggest technological civilization. The cultural diversity visible in human approaches to science, technology, and exploration would present complex patterns for external analysis. Different nations pursue varying strategies for space development. Scientific investigation follows diverse methodological approaches, and technological innovation emerges from multiple competitive and collaborative frameworks. Such diversity might be interpreted as either strength, that provides resilience and adaptability, or weakness that prevents unified action on planetary scales. The educational and research infrastructure that supports human scientific advancement would be clearly visible through its electromagnetic signatures and space-based activities. University research programs, government laboratories, and private sector innovation all contribute to accelerating technological development, while international scientific collaboration creates networks that span political boundaries. The investment patterns visible in research priorities would reveal human assessments of promising technological directions and potential solutions to current limitations. The philosophical and ethical frameworks that guide human space exploration would be evident in the protocols governing planetary protection, the international agreements regulating space activities, and the careful consideration given to potential environmental impacts of space development. Such frameworks suggest a species beginning to grapple seriously with the responsibilities that accompany advanced technological capabilities, though the extent of this wisdom would require extended observation to assess accurately. As 3I/Atlas continues its approach toward the most critical phase of its solar system encounter, it maintains the perfect position for observing not just humanity's current state, but the trajectory of our development toward whatever we might become. The decisions we make about space exploration priorities, environmental stewardship, and international cooperation during this crucial period might well determine the conclusions drawn by any intelligence that might be conducting such comprehensive assessment of our civilization's potential. The gentle observer from the depths of space carries with it perspectives shaped by experiences that span the evolution of our galaxy itself, witnessing the birth and death of stellar systems while accumulating wisdom about how intelligence emerges and develops across cosmic scales. If such extended reconnaissance has indeed been its purpose, the observations gathered during its passage through our solar system would represent just one chapter in a vast library of galactic intelligence. Our particular combination of promise and limitation, adding another data point to understanding the complex processes that govern civilizational development throughout the cosmos. The question that resonates through the quiet corridors of observatories around the world is whether 3I/ATLAS represents merely the latest in a long series of such reconnaissance missions, or perhaps something more immediate in its implications for humanity's future. The timing of its arrival, coinciding with our emergence as a technological civilization capable of detecting and studying interstellar visitors, might reflect either remarkable cosmic coincidence or more deliberate coordination designed to assess our readiness for contact with intelligences that have already mastered the challenges of interstellar travel and communication. The cosmic perspective that billions of years of galactic wandering would provide might reveal patterns in civilizational development that remain invisible to species confined to single stellar systems. The environmental crises, technological transitions, and social evolution that characterize emerging civilizations might represent common phases that all successful spacefaring species must navigate, with the outcomes determining whether they achieve long-term survival and cosmic significance, or join the countless failed experiments scattered throughout galactic history. The patience required for such extended observation suggests intelligence that has learned to think in terms of stellar lifetimes rather than biological generations. Strategic planning that encompasses not just technological development, but the deeper wisdom necessary for peaceful coexistence with other advanced civilizations. The careful balance between gathering necessary intelligence and avoiding premature interference might represent protocols refined through millennia of interstellar diplomacy, standards developed through experience with countless species at various stages of cosmic awakening. The implications of being subject to such comprehensive surveillance extend beyond questions of privacy or sovereignty to fundamental considerations about the nature of consciousness, communication, and community on galactic scales. If advanced civilizations regularly monitor developing worlds, the ethical frameworks governing such observation would necessarily reflect sophisticated understanding of the delicate processes that govern successful transitions from planetary to interstellar civilization. The decision to maintain concealment while gathering intelligence might represent not indifference, but rather profound respect for the autonomous development that successful spacefaring civilizations require. The data that 3I/ATLAS continues to accumulate as it journeys through our solar system, whether representing natural processes or something far more sophisticated, contributes to humanity's growing understanding of what travels between the stars and what such travelers might observe about the worlds they encounter. Each spectroscopic measurement, each trajectory calculation, and each electromagnetic signature detected adds to our knowledge of cosmic phenomena, while simultaneously raising questions about the boundaries between natural and artificial processes. In a universe where advanced technology might be indistinguishable from the most sophisticated natural systems, the story that emerges from careful analysis of this cosmic visitor reveals complexities that challenge our most fundamental assumptions about the nature of intelligence, observation, and contact between civilizations. Whether 3I/ATLAS represents the patient wandering of ancient cosmic debris or the most sophisticated reconnaissance mission ever conducted in our stellar neighborhood, its presence serves as a reminder that the universe contains phenomena that operate according to scales and principles that stretch the boundaries of human imagination. The gentle wanderer continues its silent approach through our cosmic neighborhood, maintaining optimal positioning for whatever observations or activities its true nature might require, while humanity struggles to understand whether we're witnessing natural processes playing out according to familiar physical laws, or our first encounter with intelligence that has mastered the art of hiding among the ancient objects that drift between the stars, watching and waiting with patience that spans the ages of worlds. The months that stretch ahead of us carry within them the promise of answers, though perhaps not the ones we expect or even desire. As 3I/Atlas continues its stately progression toward that moment when it will slip behind our sun's brilliant shield, we find ourselves in the peculiar position of witnesses to a cosmic drama whose final act will unfold beyond our ability to observe. The irony is not lost on those who spend their nights peering into the depths of space, that our most sophisticated instruments will be rendered temporarily blind, just as this ancient wanderer reaches the crescendo of its solar encounter. The approaching conjunction represents more than mere astronomical mechanics. It marks a threshold where human knowledge meets the fundamental limits of observation, where our carefully constructed theories about natural versus artificial phenomena will face their most stringent test in the privacy of solar concealment. The electromagnetic storm that surrounds our star creates a natural sanctuary where activities might unfold according to principles we have yet to discover. Processes that could reshape our understanding of what constitutes possible in the vast theatre of cosmic phenomena. Consider the delicate dance of gravitational forces that will embrace 3I/ATLAS during these hidden months. The sun's immense mass creates distortions in space and time that could serve purposes far beyond simple orbital mechanics. General relativity teaches us that such extreme gravitational environments offer opportunities for effects that operate according to principles barely glimpsed by human science. Time dilation becomes measurable. Space itself warps in ways that could facilitate communication or navigation techniques that transcend our current understanding of physics. The solar wind that streams continuously outward from our star carries with it charged particles and magnetic field lines that create a complex plasma environment, unlike anything found in the quieter regions of interstellar space. For natural objects, this represents merely another environmental challenge to endure. For anything more sophisticated, it might provide the perfect medium for activities that require the unique conditions found only in the gravitational embrace of stellar cores. The radio interference generated by our sun's natural emissions would mask most artificial signatures from Earth-based detection, creating what amounts to a natural stealth field that could conceal communication bursts, navigation adjustments, or sensor deployments that might otherwise risk revealing the true nature of whatever travels beneath 3I/ATLAS's dusty camouflage. The solar plasma itself might serve as a medium for information transfer methods that operate according to principles we have yet to theoretical frameworks to comprehend. During these months of concealment, the object's trajectory will carry it through regions where solar heating reaches intensities that would challenge even the most sophisticated thermal management systems. The sublimation rates of surface materials will accelerate dramatically, creating particle streams and chemical emissions that could serve dual purposes as both natural phenomena and operational camouflage for activities that require concealment from external observation. The organic compounds that stream away from the hidden nucleus during this period will undergo chemical transformations driven by intense ultraviolet radiation and particle bombardment. These processes create exactly the kind of complex chemistry where the boundaries between natural and artificial phenomena become most difficult to distinguish. Advanced molecular engineering might employ these same pathways for purposes that remain invisible to observers, lacking appropriate theoretical frameworks for recognition. The gravitational dynamics of closed solar approach offer possibilities that extend far beyond simple orbital mechanics. The Oberth effect, where propulsive efforts achieve maximum efficiency when applied at points of maximum gravitational influence, could enable course corrections or velocity changes that would be impossible to achieve through conventional means. For natural objects, this represents merely another consequence of gravitational physics. For artificial systems, it might provide the perfect opportunity for maneuvers that serve strategic purposes while remaining indistinguishable from natural perturbations. The magnetic field environment near our Sun creates conditions that could facilitate exotic physics experiments or communication techniques that operate according to principles barely touched by human science. Magnetic reconnection events, plasma instabilities, and the complex interactions between charged particles and electromagnetic fields all combine to create a natural laboratory where advanced technology might conduct tests or gather data that would be impossible to obtain elsewhere. The thermal environment during close solar approach will subject any technology to stresses that would test the limits of even the most sophisticated material science. The temperature gradients, thermal cycling, and intense radiation exposure create conditions that would challenge systems designed for the cold stability of interstellar space. Yet these same conditions might provide necessary activation energy for processes that remain dormant during the long centuries of cosmic wandering. The particle bombardment from solar wind and cosmic rays during this period will reach intensities that could trigger responses in systems designed to remain quiescent under normal circumstances. Radiation-hardened electronics, self-repair mechanisms, or adaptive materials might all respond to such extreme conditions in ways that reveal their artificial nature. Yet these responses could easily be attributed to natural processes operating under extraordinary environmental stress. The electromagnetic spectrum during solar conjunction becomes a cacophony of natural emissions that would overwhelm most detection systems designed for the quieter conditions of deep space observation. Yet within this apparent chaos might lie encoded information, navigation signals, or communication protocols that operate according to frequencies and modulation schemes that remain invisible to civilizations lacking appropriate technological sophistication. The gravitational lensing effects possible during close solar approach could enable observation techniques that transcend the normal limitations of distance and resolution. Our Sun's mass creates distortions in space-time that can focus electromagnetic radiation in ways that effectively create a natural telescope of enormous power. Any intelligence capable of positioning itself properly within this gravitational lens system could achieve observational capabilities that dwarf conventional approaches to long-distance surveillance. The orbital mechanics governing 3I/ATLAS's passage through the inner solar system reveal trajectory optimization that would challenge our most sophisticated mission planners. The sequence of planetary encounters, the timing of solar approach, and the exit vector that will carry it back toward interstellar space all combine to create what appears to be either remarkable cosmic coincidence or perhaps the most elegant example of gravitational navigation ever witnessed by human observers. The re-emergence of this cosmic visitor from behind solar concealment will mark a crucial moment in our understanding of what travels between the stars and what such travelers might accomplish during their passage through stellar systems. The object that appears in our telescopes in December might exhibit characteristics that challenge our most fundamental assumptions about the relationship between natural and artificial phenomena, or it might continue its journey unchanged, leaving us with questions that may never find satisfactory answers. The data that will stream back from our observational networks during those critical weeks of reappearance will be scrutinized with unprecedented intensity. Every spectral line, every brightness variation, and every trajectory deviation will be analyzed for clues that might distinguish between natural processes playing out according to familiar physical laws and something far more complex disguised within the comfortable familiarity of cosmic debris. The scientific protocols being developed for this observation campaign represent humanity's most sophisticated attempt to peer beneath the veil of natural phenomena and detect signatures that might indicate artificial intelligence operating within our solar system. Radio telescopes will scan for electromagnetic emissions that exceed natural background levels. Infrared sensors will monitor thermal signatures that might reveal internal heat sources, and optical instruments will track any deviations from predicted orbital behavior. Yet the challenge remains that any technology sufficiently advanced to conduct interstellar reconnaissance would likely possess camouflage capabilities that operate according to principles we have yet to discover. The absence of obvious artificial signatures might indicate natural processes at work, or it could suggest engineering sophistication that renders detection impossible using current methodologies. The philosophical implications of such advanced stealth technology extend beyond simple questions of observation to fundamental considerations about the nature of reality itself in a universe where sufficiently advanced intelligence might be indistinguishable from natural processes. The theoretical frameworks required to analyze data from such unprecedented observations push the boundaries of multiple scientific disciplines simultaneously. Astrophysics, materials science, information theory, and even consciousness studies all contribute perspectives that might prove essential for understanding what we observe. The interdisciplinary nature of such analysis reflects the complexity of phenomena that exist at the intersection of natural processes and potential artificial intelligence operating on cosmic scales. The implications of confirmation either way carry consequences that extend far beyond academic curiosity about interstellar objects. If 3I/Atlas represents natural phenomena, it would still constitute the most remarkable cosmic visitor ever observed, challenging our models of planetary formation, stellar evolution, and the processes that govern material ejection into interstellar space. If it represents something more complex, it would mark humanity's first confirmed encounter with intelligence that has achieved capabilities we can barely imagine. The international cooperation required for comprehensive observation of this re-emergence demonstrates humanity's capacity for coordinated response to phenomena that transcend national boundaries. Space agencies, research institutions, and observational networks around the world are contributing resources and expertise to what amounts to our most ambitious attempt to understand cosmic visitors. Such cooperation might itself serve as an indicator of our readiness for contact with intelligences that have already mastered the challenges of interstellar communication and coordination. The philosophical questions raised by 3I/ATLAS extend beyond simple considerations of detection and analysis to fundamental issues about the nature of consciousness, intelligence, and communication on cosmic scales. If advanced civilizations regularly conduct reconnaissance of developing worlds, the ethical frameworks governing such observation would necessarily reflect sophisticated understanding of the processes that enable successful transitions from planetary to interstellar civilization. The concept of informed consent becomes complex when applied to surveillance conducted across such vast differences in technological capability. Any intelligence capable of interstellar reconnaissance would possess observational methods that operate beyond the detection capabilities of developing civilizations, creating fundamental asymmetries in awareness and capability. The decision to maintain concealment while gathering intelligence might reflect not indifference, but rather profound respect for autonomous development processes that successful spacefaring civilizations require. The temporal perspectives required for such extended observation missions suggest intelligence that operates according to planning horizons that encompass stellar evolution itself. The patience necessary for monitoring civilizational development across the timescales of technological emergence would require frameworks for strategic thinking that transcend biological limitations. Wisdom accumulated through experience with countless species at various stages of cosmic awakening. The database of galactic intelligence that such extended reconnaissance could accumulate would represent information resources of staggering proportions. Comparative studies of civilizational development, environmental management strategies, technological progression patterns, and social evolution processes would all contribute to understanding the complex factors that determine whether emerging species achieve long-term survival and cosmic significance. The assessment criteria applied to evaluate developing civilizations would likely reflect the accumulated wisdom of species that have successfully navigated the transition from planetary to interstellar capabilities. Environmental stewardship, technological wisdom, social cohesion, and capacity for peaceful interaction with other intelligences would all factor into determinations about appropriate contact protocols and timing for revelation of extraterrestrial presence. The current state of human civilization presents a complex profile for any such assessment. Our rapid technological advancement, growing space exploration capabilities, and increasing awareness of cosmic possibilities all suggest a species approaching readiness for broader galactic contact. Yet our environmental challenges, social conflicts, and military applications of advanced technology might indicate a civilization still learning to manage the responsibilities that accompany powerful capabilities. The search for extraterrestrial intelligence conducted by human scientists demonstrates our active preparation for the possibility of contact with cosmic neighbors. Radio telescope arrays, signal analysis protocols, and international agreements governing response procedures all indicate a civilization that has given serious consideration to the implications of confirmed extraterrestrial communication. Such preparation might influence decisions about appropriate methods and timing for any eventual revelation of intelligence presence. The space exploration programs that increasingly characterize human activities beyond Earth demonstrate systematic approaches to understanding our cosmic environment. Robotic missions to multiple worlds, space-based observatories studying distant phenomena, and plans for permanent settlements beyond our home planet all suggest a species committed to expanding its presence throughout the solar system and eventually beyond. The electromagnetic signatures that continuously emanate from our technological civilization provide comprehensive information about human capabilities and priorities. Power generation and distribution networks, communication systems, transportation infrastructure, and industrial processes all create detectable patterns that reveal the scope and sophistication of our technological development. The rate of change in these signatures indicates acceleration that might fundamentally alter our cosmic significance within decades rather than centuries. The biological signatures that Earth broadcasts into space tell detailed stories about the nature and extent of life on our planet. Atmospheric compositions that indicate active biological processes, seasonal variations driven by vegetation cycles, and the complex chemistry of a world where life has achieved remarkable diversity, all clearly mark our planet as exceptional in its biological richness and potential significance. The cultural diversity visible in human approaches to science, exploration, and international cooperation presents complex patterns that might be interpreted in various ways by external observers. Our capacity for collaborative investigation, balanced against competitive innovation, peaceful cooperation alongside military preparation, and environmental concern competing with resource exploitation, all suggest a species grappling with fundamental questions about priorities and values. As the months pass and 3I/ATLAS approaches its moment of concealment behind solar brilliance, humanity finds itself in the remarkable position of potential subject rather than mere observer. If this cosmic visitor indeed represents intelligence capable of comprehensive surveillance, we are witnessing not just astronomical phenomena, but perhaps our first systematic evaluation by civilizations that have already achieved the capabilities we struggle to attain. The questions that echo through research institutions around the world extend beyond simple curiosity about the nature of this particular object to fundamental considerations about our place in a universe that might be far more populated with intelligence than our current isolation suggests. The decisions we make about environmental stewardship, technological development, and international cooperation during this critical period might well be observed and evaluated according to standards that could determine our future inclusion in or exclusion from broader galactic communities. The gentle wanderer continues its patient approach through our cosmic neighborhood, maintaining optimal positioning for whatever observations its true nature might require. Whether it represents the most remarkable natural object ever discovered, or our first encounter with intelligence that has mastered the art of reconnaissance among the stars, its presence serves as a profound reminder that the universe contains phenomena that operate according to scales and principles that challenge the boundaries of human comprehension. The approaching conjunction carries with it the promise of either answers or deeper mysteries, resolution or greater complexity, understanding or the humbling recognition that some questions may forever remain beyond our ability to resolve with certainty. Yet in that uncertainty lies perhaps the greatest gift that 3I/Atlas offers us, the recognition that we live in a cosmos far more wondrous and potentially populated than our current knowledge encompasses. The story continues to unfold in the depths of space, written in the language of gravitational dynamics and electromagnetic signatures, chemical emissions, and orbital mechanics. We remain observers of this cosmic drama, witnesses to phenomena that blur the boundaries between natural and artificial, between the familiar and the impossible, between what we think we understand about the universe and what the universe might actually contain. The gentle observer from the ancient depths maintains its silent vigil, watching our world turn beneath changing skies while carrying within its mysterious structure either the accumulated wisdom of geological ages or simply the patient testimony of time itself, made manifest in ice and starlight. The distinction between these possibilities becomes ever more elusive as we peer deeper into the data streams that flow from our most sophisticated instruments, each measurement adding layers of complexity to questions that may define humanity's future among the stars. In the quiet hours when telescopes track this visitor's steady progress across our skies, when spectrometers pass the chemical signatures streaming from its hidden heart, when computers process the vast data sets that chronicle its passage through our solar system, we find ourselves confronted with the profound realization that we may be living through one of the most significant moments in human history. Whether that significance lies in our discovery of the most remarkable natural object ever observed or in our first encounter with intelligence from beyond the stars, the gentle wanderer named 3I/ATLAS has already transformed our understanding of what travels between the worlds and what such travelers might see when they look back at us. The cosmic dance continues, patient and eternal, carrying within its ancient rhythms either the whispered secrets of deep space or perhaps something far more profound, watching and waiting with the endless patience that only the cosmos itself can teach, while we struggle to comprehend whether we are alone in our observations or whether somewhere in the depths of space, something is observing us in return. And so we find ourselves at the end of our gentle journey through cosmic mysteries, having followed this ancient wanderer from the depths of interstellar space to the very heart of our solar system. We've traced the delicate threads that connect observation to wonder, science to speculation, and perhaps most intriguingly, the familiar to the utterly unknown. Whether 3I/ATLAS represents the most remarkable natural object ever discovered, or something far more profound watching us from the depths of space. It has already given us the greatest gift any cosmic visitor could offer: the reminder that we live in a universe far more mysterious and potentially populated than our daily lives would suggest. As you drift towards sleep tonight, perhaps you'll find comfort in knowing that somewhere in the darkness above, this gentle observer continues its patient journey, carrying with it either the accumulated wisdom of billions of years spent crossing the galaxy, or simply the quiet testimony of time itself made manifest in ancient ice and starlight. The distinction between these possibilities may forever remain beautifully, tantalizingly beyond our grasp, and perhaps that's exactly as it should be. The cosmos keeps its secrets well, but it shares just enough wonder to remind us that every night, sky holds mysteries waiting to unfold like whispered promises in the dark. Sweet dreams, fellow travelers, and may your own journey through the night be filled with the same gentle mysteries that dance between the stars. Journey through the night be filled with the same gentle mysteries that dance between the stars.